stand. This is match stand for the stands for. I know what it really stands for. They kind of stand for. This is metro area philosophers of science. So we've had it, it's gone on for about 6 years, and we've had lots of very nice talks in it, including people like Temporal, Nonlocality, and but today we have sort of a fantastic star-studded cast of Eddy, Chen, and Adlam, and Maudlin. So I hope MAPS continues. One of the people who's been helping me with it said he would come. He's from Fordham. Hope you can get in.
Peter?
Where's Diego? Where's Diego went down? You think, he seemed to be letting people in.
He was letting people in.
Yeah, he was super easy.
Okay, so Peter's coming. Yeah. Okay, so I'm not sure what's going to happen with this, but I will do some of it next year, but I really like the vacation. And I hope some other people want to continue with this. And in fact, where's Vishnu? Vishnu had the cool idea that we might expand things a little bit and have a kind of reading group as well, people interested in philosophy of science more generally. And we also think about there's a probability group that's been going on, so maybe we'll expand into that. There must be enough people in the area who should really be interested in such a thing. So I hope it goes on. Next year, we're going to have one more meeting this year, May 9th. I think that Jean Guzman will be here. I'm not sure which room it's going to be in, but he's visiting Tim, Chen, and stuff like that. So he's going to give a talk here then. That'll be the last one for this year. This year, I knew Eddy was going to be here, and Eddy had decided to tell us about something which is what he did is he took the Wentaculus and he turned part of it upside down. So he's going to tell us about that in a minute. Another important thing to say. I was sort of remiss about actually arranging things because there was a big conference on the weekend I'm involved in. So I made a reservation at a restaurant, and that's near here. I wonder whether anyone's eaten it. You guys might have K1U.
No.
It looks good.
Where is it?
Just on Lafayette, not very close to this. It's a sort of Asian barbecue, Korean barbecue, fancy.
Korean barbecue? No, that's always
Korean barbecue and other kinds of fancy Asian stuff. Okay, so I made a reservation for 8 because they told me that if some people didn't show up, I'd be charged anyway. And but if more people want to come, we got to do something about that. But the MAPS has funds. I'm not sure I should say who's thanks for it unless he gives me a nod. But one of the people here gave support. I don't want to embarrass him by saying this, but maybe he'd be perfectly fine. He's not doing anything, so I won't say it. And so we have some funds. We haven't spent very much of it, but we've used it in part to feed these speakers. But I think today, 8 people can be fed at this place. Because about that many speakers and their spouses and so on. I think. Well, I don't want to be unfair. Anyway, the speakers and the spouses and the people who are the organizers, and Diego. Diego also is a Rutgers graduate student who helps him exist and so survive. And so he's going to come too. Okay, so if other people want to come at some point in this little break here, just tell me and I'll count up the number of people. And if we need to enforce the reservations, we can do it. I think it's a pretty good place. It's also not especially cheap. I guess it would be $40 to $50 a person. So it seems very okay. So we're going to have 3 really interesting talks about issues and foundations of quantum mechanics. They're somewhat interconnected. I asked the people who give the speaks to try to keep their talks like about 40 minutes, but no one's going to keep them doing that, I guess, or maybe I would say something. So we have a lot of time for discussion because there are not a number of other people here who are very interested in these subjects. So with that, Eddy, one second.
Thank you so much, Barry. Thank you, Diego, for organizing this event. It's great to be back in maths. I used to be one of the graduates helping Barry organize maths for a few years. It's always good to come to maths talks. I learned something new. Many of my ideas grew from events, discussions with this group, and many of you. So this project, the Wentaculus was parsed upside down, but the Wentaculus started about 5-6 years ago in the grassroots records. And through discussions in this group, and especially with David, Barry, and Tim, and Vishnu, and among others, I started wondering if I really understand quantum mechanics or the error type. I realized I don't, and I can't, honest to God, to be a realist anymore if I don't understand this quantum mechanics business. So I started working and playing around, trying different things, talking to different people. When I discovered this formalism of density matrix stuff from Shelley in a paper that almost no one discusses in philosophy conferences, but it's a really cool, interesting, elegant, and actually not too long paper, published Foundation of Physics, the journal, 2005, called On the Role of Density Matrices in Bowing Mechanics. Different roles, different objects, different kinds, and distinctions very carefully laid down. And surprisingly, all the ideas, some of the ideas go back to Bell on his discussion for density matrix in Bowing Mechanics. And I realized this is the perfect vehicle to combine certain ways to think about quantum mechanics and the thermodynamic error of time, especially Wentaculus paradigm. It's different from the wave function picture, and different from the Boltzmann and Wentaculus. But there are combinations and connection to both of them. Okay, so today I want to discuss, actually, hopefully to summarize, because I want to talk for 40 hours. Obviously, that's impossible, and there are many themes and details I want to talk about. But I can't, so I'm going to talk for 40 minutes and very fast, and only give you a survey in the landscape view of the whole idea and the viewpoint in general. So I'll talk very loosely and speak many falsehoods to convey a general viewpoint in the vision. Okay, but we'll talk more about details in Q&A. All right. Before I begin, I would like to dedicate this talk and this paper version to the memory of Adlam Dual. As many of you know, he had a huge impact on the field of quantum foundations, philosophy of physics, and he had a huge impact on me as I think about these issues. He sadly passed away 2 years ago due to COVID. I was shocked with the news. I was corresponding with him just about these issues right before COVID stuff happened. So it was very sad news. Yeah, so he's not only a great mathematician, great physicist, but also a great philosopher. And above all, he's a great, wonderful human being. So I really miss him. This paper version is actually forthcoming and in a volume in memory of Adlam, edited by Shelley, Roddy, I think Angelo, Nino, among others. So I think it is fitting. Okay, let me start. Two of the most difficult problems in the foundations physics are, first, what gives rise to the error of time? And second, what is the ontology of quantum mechanics? Well, there is quantum mechanics. And the answers, one, involves the past hypothesis of the initial low entropy state or boundary condition of the universe. And second, in terms of quantum state realism about waving. This is what makes everything happen in the quantum world. It is part of the ontology of the quantum state, the furniture of the universe somehow, either as a field or a law or something else. Now, the conventional wisdom is that these two puzzles, quantum ontology and times error, are independent puzzles. Are they really independent? I suggest that a new way to understand the second, the quantum ontology, gives us a better way to solve the first, and both will become better in this way. And the key is what I call density matrix realism. The idea that the quantum state of the universe is objective. It can be pure or impure. I'm going to unpack this later. And by the way, I was working on this and I gave this phrase density realism, but this idea came much earlier. The definition of this is actually not the same one as I used in my first paper, so I actually try to refine this a bit more in later works. Okay. In this talk, I want to discuss a new way of thinking about time zero in the quantum universe that presents a more unified solution to both puzzles and brings together the foundations of quantum mechanics and statistical mechanics. And I think with interesting implications, open questions for both physics and philosophy. I call the theory the Wentaculus. I'm going to explain why it is called the Wentaculus in a second, but mostly it is this word W for density matrix. So that's why it's the Wentaculus. Okay, now a tree is known by its fruits. The Wentaculus, I think, I argue, shows that density matrix realism is really nice. It's theoretically fruitful because of the simplicity that it allows us to postulate the quantum state, exactness of boundary condition, and potential unification of different domains of physics, system mechanics and quantum mechanics. Different kind of probability become one. And also enables some version of strong determinism, as long as the quantum history is concerned. Perhaps quantum realists, those who are realists with quantum mechanics, should be, or at least consider, density matrix realism. Perhaps they should be a density matrix realist. Okay. Now the upshot is that quantum state universe may well be fundamentally impure, density matrix, simple, gnomic, on powers of laws. Okay. A different way I might title this talk would be The Wentaculus, or How I Learned to Stop Worrying and Love the Quantum State. Okay. Because really this is how I tend to lay down some of my worries about quantum realism. Okay. Here's the overview. I will characterize what density matrix realism is. In a companion paper promised in the volume edited by Kufaro and Hartman, I'm going to kind of elaborate this more, but in this talk, it's going to say briefly about density matrix realism, and then the standard wisdom regarding error time and the past hypothesis paradigm, and come to the Wentaculus in the third section. Okay, so what is density matrix realism? Again, it is the idea that the quantum state of the universe is subjective. It can be pure or impure. Let me unpack this. The means unique. I really mean unique. There is one, not two, not three, not four. Okay, one. This is important because, for example, David Wallace has postulated a version of quantum state realism that has two quantum states, one pure, one mixed. That's not my view. And also, some people sometimes misunderstand this view. Perhaps, Yao Shan is one of them, who sometimes regards this as saying there are two quantum states. No, just one. Just one single quantum state for the world. And I'm focusing on the quantum state of the universe, W. Emphasis, the universe. So there are quantum states for the subsystems. This room, this galaxy, the conductive ones, or effective ones, or reduced ones. But I'm focusing, this thesis is primarily about the quantum state of the universe. Even on standard quantum mechanics wave functions, there are no controversies that many subsystems are given only by impure states. But here I'm thinking about the quantum state universe. Okay. And that is a different status, different kind of idea, and it's controversial, I think. Objective. What does that mean? I'm leaving this open-ended. In part because I want this to be a way we can talk about quantum state realism in general. And this kind of echoes the point that Sean Goldstein and Tim Maudlin have made in other works, that there was one way to be a wave realist, for example, is to think of this as a particular kind of high-dimensional field. That's the way that David Albert and Elizabeth Ney understand wave realism. But in a general sense, a realist can take the quantum state to be a wall, or some ontologically distinct category, like Tim's view, and they can all be realists of the quantum state.
Can I just ask a clarifying question?
Yeah.
You can think of it as a property of the universe?
You may. Yeah, it's like a physical property of the universe.
It could just be universe has property, it's just not a property, it has, in virtue of the universe having parts with other properties.
Right, that's right. So there can be objective sort of aspects. Say a field, that's somewhat objective and can compare that cases. Or you think the law. It's insofar as laws are objective for even humans and non-humans, of course. We can think of a nomological interpretation of the quantum state as a version of quantum state realism. Okay, sorry. And can be is a modal notion, although this modal notion is more general than nomological necessity, or nomological possibility. Because I am not fixing the laws yet. I'm giving you a framework for the thinking about ontological quantum mechanics. And this can be more general because there are different versions of the laws. Say Wentaculus or quantum Nonlocality, they have a similar kind of ontological mixed state, but they have more a wider or narrow class of nomological possibilities. So can be here is somewhat permissive, pure or impure. So on this definition, the quantum state universe can be pure. That kind of overlaps with realism, but it can also be impure. That's something ruled out by wave quantum realism. So this is how I define waveform realism in my paper in Fawcett Compass. But it's different from the way that David Albert and Alyssa Ney usually define waveform realism. But it's a terminological difference, so it's not a conceptual difference.
But if it's a property at a time, is it temporally indexed? That would make it differently from the way we think about laws.
Right, it is, well, it depends, I think. Even then, there could be questions about how to get a nomological interpretation of quantum state. Yeah. Okay. So objectivity here is open-ended as long as it's not mind-dependent or somehow subjective. So I'm ruling out quantum Bayesians here. And there's interpretations like information theory. But this leaves open the nomological view, the material ontology view, say Maudlin's kind of ontological category of quantum state view. All of them can be part of this family of realism. Okay. There were proposals already, but I didn't actually appreciate or understand before I started working on this project. They are already kind of versions of density matrix realism. And I think the most important one for me was reading this paper by Adlam, Shelley, Roddy, and Nino, 2005, physics, posted a year ago, before this publication. And it's a great paper. Okay. And there are other papers by Moroni at the same time, same journal, David Wallace, and there's a follow-up paper by Valia Lori, Shelley, Roddy, and Nino in PJPS that extends this density matrix, fundamental density matrix to GRW and to even versions of average. So we have Bohmian version, GRW, and average version in these two papers. I think David will talk about this a little bit too in the case. There's a very nice paper recently by Katie Robertson, and she is taking on the Gibbsian view of system mechanics. And she also uses certain kind of aspects of density matrix realism. I am not a Gibbsian, I'm kind of hardcore Boltzmannian. But I still want to kind of highlight her contribution here. Well, now to take kind of it's warm up because some of you appreciate the wave function realism theories, and it's more familiar. So let's start with this. Think about let's call Bohmian mechanics not Bohmian mechanics, but psi prefix to signify the difference. Psi Bohmian mechanics means Bohmian mechanics with the laws that refer to a universal wave function, Schrodinger equation, guidance equation, quantum distribution in terms of the wave function T0, and other properties. And this psi average, the Schrodinger equation, made plus primitive ontologies. And psi version of GRW collapse theory, you have Schrodinger equation interrupted randomly at random times by this collapse mechanism. You have post-collapse wave function from a pre-collapse wave function acting on by this collapse operator divided by the mobility constant. You have the post-collapse wave function. So we have psi version of Bohm average GRW solution. In parallel, we have that's called W Bohmian mechanics, W average quantum mechanics, and W GRW collapse. And these are less than. Let's look at the fundamental equations. So for W Bohmian mechanics, you have a configuration for n particles moving in free space, say, start in this case, and replacing the psi with a double density matrix. In general, can be pure or mixed. And this W obeys a deterministic linear von Neumann equation with its Hamiltonian operator. The generalization Schrödinger equation, you basically derive it without the principles. And the W evolves over time, deterministically, and W will guide the particles. It spits out the gradient of this, spits out a velocity field configuration space. And it's taking gradient of the density matrix in the position representation here. So I'm being lazy here because you can write this in terms of positions or the operator formalism. And here I'm going to expand it. The position representation in Q prime and T, setting Q prime equals Q, the actual configurations. And this gives you a velocity field. So plug in Q at T0 and W at T0, you just evolve the deterministic of time. And that's how you can think about this picture. And moreover, you stipulate either by some arguments or by as an axiomatic law that the initial particle distribution of Q's is in terms of the density matrix, setting Q equals to Q at T0. And that's the kind of generalized version of quantum equilibrium distribution in the case of a density matrix. When it's pure, it's like psi naught squared. When it's mixed, it can be something more general. Okay. The algorithmic quantum mechanics is even simple. You don't even have particles, just have a dot evolving entirely in time by the von Neumann equation. And you can add a primitive ontology or three-dimensional ontology, say mass density. In the same way, you might add a mass density to the usual version of W. This is sometimes called Schrödinger's first theory with M, so Sm. So Allore and co-author is called Sm. But Sm applies to density matrix. Then you have defining the density mass density function in the same way as you do in GW as a trace of the mass density operator acting on W at time t, with defined in the usual way. So you can have two versions of W average. One is just quantum state, and two, dualist version, quantum state and something derived from quantum state or dependent on quantum state, the meta density ontology. The GW version of density matrix realism looks like this. You have the linear evolution of density matrix by the Schrödinger equation is interrupted randomly with rate n, lambda. N is the number of particles in both. And lambda is a new constant nature, the rate collapse. By collapses, the post-collapse density matrix, if it's given by the pre-collapse density matrix, actually sandwiched by this collapse rate operator divided by this normalization constant, with the density matrix giving you a distribution of the collapse center. And the collapse rate operator defined in the usual way as on the wave function version of GW. Again, you can add local variables to this, say primitive ontology like matter density field or the flashes at the center of the collapses. You can do three versions. WGRW0, WGRWM, WGRWF, right? Now, let's think about two issues here. One is the nature of the quantum state, and two is empirical equivalence. First, the key question, what does the universal quantum state represent? Depends on which theory it takes seriously and endorse or consider. The psi version and the W version. Well, there's one way to understand the quantum state, which I find very attractive. Although I became worried about it after, Chen and Eddy and David Presley doing perspective defense many years ago, which is, that is, if you take the nomological view, quantum state represents something like a wall. It's not the same as a paradigm principle. It has time dependence in general. And for the intervallic problem, it seems a bit odd, right? Given just particles alone, how do you solve equations, right? I think they both are versions of what I call the problem of complexity. That is, there's something about the quantum state in this understanding is too complex, too time dependent, too unwieldy to be a law, and that doesn't conform to our view expectation of the law to be simple. Simple description, like ethics and Schrödinger, that's very simple law. Now, as I argue, whether the quantum state is pure or impure can make a difference to its complexity or simplicity. It's not obvious yet. It's only obvious when you add the path hypothesis, I think. Okay, second issue, empirical equivalence. Is wave function realism empirically equivalent to density matrix realism? Do they make the same predictions for all possible observations? For example, is psi versus Bohr mechanics empirically equivalent to W versus Bohr mechanics? That's not very precise yet. But when we make it more precise, say the psi Wentaculus Bohr mechanics versus the W Wentaculus Bohr mechanics, the question becomes more precise. And I do think that, yes, the two are empirically equivalent. They make the same prediction on all observations. Now, if they're not empirically equivalent, then we have different predictions for experiments. Okay, we'll come back to this point later, maybe in Q&A. And I think, one way to understand some of, Davis' work in his new book manuscript, against the real, I think, right? Mm-hmm. Against the real.
Yeah.
Is that it is worried about empirical confirmation, empirical equivalence here in a deeper way. It's not just equivalence in observations, but something a bit more substantial. So we'll come to this point maybe later. Okay. Now, regarding the error of time, let's say briefly, because all of you probably are familiar talking with Barry and David on how the Wentaculus view works. But there are a few things I want to clarify or highlight that sometimes is neglected. First, we have macroscopic reversibility, thermodynamics, and so on. And second, you have microscopic reversibility, dynamical laws, fundamental laws. And that seems to be a bit odd. Now, the past hypothesis adds, by fiat, this new axiomatic law. The universe started in a low entropy state. The axiom and the law in the theory. Given this, you might expect the natural realization is one with higher entropy. Now, there are questions about the past hypothesis, how we postulate the past hypothesis. In general, we should think, given, say, a classical phase space, the partition of phase space into regions of macroscopically distinguishable microstates, macrostates, right, are going to be somewhat fuzzy. It's not going to be clear-cut, precise, right? So I had Harold's picture with wiggly lines, because wiggly lines means fuzziness or vagueness here. And it's not just fuzziness, but also high order vagueness. Anyways, so the past hypothesis maps onto, say, some description of macro state at T0, call this M0. And it's going to be a fuzzy set of, fuzzy boundary of possibility on the initial phase space. What is the set of microstates corresponding to the past hypothesis? And we say X0, the initial phase point, must belong to. Bit fuzzy, bit vague. It might be a appropriate kind of vagueness, given, say, our expectations of how the past hypothesis explains. It's not explaining the precise regularities, but somewhat macroscopic regularities. Okay. The status of past hypothesis has been called into question. Well, it is axiomatic. Usually we think that it is not derived from other axioms. And it seems to be gnomic. It probably explains times error, including reliability of records and anomic patterns. But there's some potential issues. One, it's not dynamical. Some people treat this as a crucial issue. And also, there's a dilemma. That is, it seems to be a vague law and a fundamental law at that. And any way to specify this boundary is going to be somewhat arbitrary, somewhat objectively arbitrary. We can give a precise definition of that in terms of untraceable arbitrariness. That's going to be present only here and nowhere else in other precise formulations of physics. Constants of nature are somewhat arbitrary. Why is this number, not this number? But the way that the constants are arbitrary is different from the way that the past hypothesis boundary on phase space is arbitrary. And that's why I use a kind of notion of traceability here. So let me kind of illustrate this with the following diagram.
Eddie, can I just ask you a question before we get that the last slide? When you say it's gnomic, is all that you mean what comes after that whole?
No. I mean,
I don't think it's gnomic. I think it does partly explain other prime arrows. And it explains other patterns, which I actually would call gnomic patterns. So what do you mean when you say it's gnomic?
Sorry, I meant this is suggestive of gnomic, given other principles that we might have independent warrants to believe in. It's not that this is sufficient for the definition of gnomic. And I agree that I don't think there's going to be a conclusive argument that is gnomic. But nomic is definitely captures part of this. To say it is nomic, for some people who think the explanation will work in this way, but it's basically saying this. And
You think it was constraining?
no, it can be kind of systemization too. So it's can be systemization. So nomic in this way, yeah, it's neutral reality.
What are the other, what's some idea about what people think laws do?
Right. That's right.
Or-
Yeah.
But Tim, I think, would disagree with that.
That's right. Yeah, Chen would disagree with the background assumptions that lead us to argue that it is nomic because of this. Right. Okay. So why is this dilemma? Okay. So that's why I'm going to speak very loosely because there's a long paper about this in Philosophical Review last year, and I won't be able to capture the entire argument here. But the basic intuition is this. What is this arbitrariness I'm talking about? Is that if you look at this region interface, zoom in a bit. Suppose I say, okay, what about a precise version of path hypothesis? Call this the strong path hypothesis. That's going to pick out a particular boundary, a precise boundary in phase space that corresponding to the path hypothesis. Call this gamma 0. And we say that x0 belongs to gamma 0. That's my strong path hypothesis. Now, but you can also have another gamma 0 prime that's slightly different from gamma 0 in terms of the boundaries, some small differences in the boundaries, such that most points compatible with the first one will be still compatible with the second one. So changing the boundaries of the strong path hypothesis would make a difference to most points compatible with the first law. That's the sense in which it is untraceable in this way. Think about other things in physics, constants. The formula equations, f is ma, now f is ma to the power 1.001. Those things are arbitrary, but not in this way. Changing the constant g to some value different from g, even small deviations, you only change the trajectory of every object, basically, almost every object. So most microhistories compatible with one value, in general, will be incompatible with those of the laws of different value. So constants and form of laws are precise and arbitrary, but not in this way. So if you regard traceability as a consideration, as a rather theoretical virtue or something, then this is a reason to be cautious or to desire a better version that doesn't. So maybe in this case, we should postulate a vague version of path hypothesis to preserve traceability. That's the general argument. Sorry, I couldn't give you a more precise definition here. That's the intuition. So in the quantum version of path hypothesis, before the Wentaculus, the problems are actually almost the same. And there will be some more differences, some more problems given. The status of path hypothesis, non-dynamical, dilemma between nominal vagueness and entropy of arbitrariness, still present in the versions of wave function, even some version that measures Wentaculus. Also, there's going to be an interesting kind of dualism in the quantum version of the path hypothesis. There will be the quantum probabilities, like the Bohr rule and so on, from distribution postulate or so on. And there's still mechanical probabilities imposed at the distribution over possible quantum states, at T0, say. And those two will be kind of the different sources of objective probabilities in physics. That's interesting. Maybe it's, they can coexist, but it might be better to do in one way, that is to unify them in some way, to derive one from the other. This, I think, the spirit of David Hilbert's conjecture regarding GRW, you can derive stat-mech probabilities from quantum probabilities given plausible assumptions. Okay, and we'll see that in the Wentaculus you can also do this, and in a more conservative way. What makes a difference in the Wentaculus is at time t0, the quantum microstate equals in the quote, okay, equals the quantum macrostate. That's going to make a difference to how we think about traceability, arbitrariness, and probabilities. And the information in the path hypothesis in the Wentaculus is going to pick out a simple and unique density matrix. Okay, let's come to the Wentaculus. The Wentaculus is a proper subclass of density matrix realism theories. It is compatible with density matrix realism, but there are other versions of density matrix realism that don't satisfy the Wentaculus. The Wentaculus is inspired by the Nonlocality of Albert and Lower, and also writings by the Boltzmannians, Leibowitz, Jagosi, among others. Let me give a first quick overview of the classical Nonlocality. Everyone probably knows this already. We have the first dynamical law, F equals ma, and F interactions, classical interactions, and the path hypothesis. Well, there's a lot going on here because in Boltzmannian and map, you have state space, energy shell, core screening, right? Core screening gives you a set of macro states. Some are huge, the equilibrium ones. Some are very small, like path hypothesis. So you choose the small, one of the small one, particular small one, to be the represent the macro state that that kind of constrains or kind of describes the initial point, initial place point. So this version is going to be a precise gamma given a choice of C parameters. It's going to be some kind of vague parameters here. Okay, and given the path hypothesis on this, you have the statistical postulate. So we have uniform plot distribution. So the normalized volume measure, say on an energy shell, that's going to give you a plot distribution over microsets compatible with the path hypothesis. Why is it called a Wentaculus? Well, Barry's wearing the t-shirt. So I'm not going to explain this very much. But okay, here's briefly, it's coming from this movie, and I heard there's the after story of Coen brothers, the Wentaculus, and anyway, okay. So this is the probability map of the universe. That's aspiration. Okay. Now let's update the Wentaculus with the quantum mechanics. I'm going to give you three versions. Quantum Wentaculus 1, the naive version called the wave function. Quantum Wentaculus 2, the naive version called the density matrix. And the Wentaculus, which is, I think, a better version than both. Not the wave function version, and not the naive density matrix version. The quantum Wentaculus 1, replace F with a made by Schrödinger equation, replace H by H bar, sorry, H hat. And this is left open-ended. We have many interactions here. The path hypothesis is going to give you, okay, there's many things going on here. You have a Hilbert space, energy shell, given by the span of the energy eigenstates. Those energy eigenvalues are in the small spectrum, E to E plus delta E, and give you a basis and give you a subspace of the total Hilbert space. In the energy shell, you have core screening, not in terms of regions, but in terms of diagonal subspaces. So the XYZ thing, XY plane is a subspace of the XYZ coordinate space. So in this case, I'll do a 5,000 dimensional Hilbert space. A 500 one will be a subspace. 500 dimensional one will be a subspace in the Hilbert space. Now we choose a particular low dimensional subspace of the total, energy shell, given a choice of parameters. This will be, say, let's call this HPH. Now we know this is kind of some arbitrariness here because it's going to be a choice of parameters, of course, screening and so on. HPH will give you a class of wave functions. The macros are going to be similar in terms of the macro variables, assuming the low entropy value, the volume value, this size, the universe, and so on. And this will be a low dimension subspace, say 500 dimensions out of say 5 billion possible dimensions. And this is a constraint. The initial wave function belongs to this subspace. And given this, we have this following statistical postulate. We're going to postulate that there's going to be a uniform plot distribution, which is the normalized surface area measure on a unit sphere in the subspace, HPH. It's all standard. And quantum mechanics usually just been done on this. And you see a lot of results in this. And there are lots of interesting, striking similarities and dissimilarities. Theorem become somewhat easy to prove in the quantum case, like canonical locality. And that's really cool. Okay. Now, there's a naive version of the density matrix version of the quantum Wentaculus in this one. It's not a Wentaculus yet, but I want to highlight this because there's two interesting questions here. You have the von Neumann equation governing possible density matrices, and you say the constraint is that the initial density matrix is one that's concentrated inside the path of the subspace. What does it mean is the trace of the subspace projecting operator acting on the density matrix equals 1. But that's not unique, right? Give you many density matrices compatible with the path hypothesis. Now we can postulate a uniform distribution over such density matrices, and that's actually possible. I was surprised to learn this. In my master's thesis, I said this is impossible. Roddy said, no, it's possible. So I was wrong and wrote a paper about this last year, showing there is a natural Maudlin measure space of density matrices compatible with a low-dimensional subspace, a finite-dimensional subspace. Okay, now each psi pH quantum and each WPH quantum theory admits many choices of the initial quantum states. The initial subspace we assume is finite-dimensional but not one-dimensional, and that is compatible with many wave functions. And this is compatible with many density matrices. Can we do better? Can we narrow down the initial choices of quantum states in either way to exactly one? I think we can do this for the second, but maybe not for the first. At least I don't have a proposal for the first yet. Proposal: we can use the path hypothesis to pin down natural initial quantum state in the following way. First, allow ourselves to appeal to density matrix as well, to be a density matrix realist. The quantum state universe is given by a density matrix, it's objective, rather than a wave function. And it can be pure or impure. I'm here thinking about impure case. And moreover, there's a natural density matrix in the subspace. The subspace corresponds to the passive part of the subspace, namely the projection normalized by dimension of density matrix. This is the simplest object you can write down for any kind of dimensional subspace. It is basically the matrix, diagonal matrix with a block with 1, 1, 1 in this block and 0 outside the dimensional subspace. And divided by a number, say k is the dimension, the number is 1 over k in every entry in the block. And this is the normalized projection onto the subspace. Add this proposal to density matrix realism, then we have the Wentaculus. So there are two laws of the Wentaculus, two fundamental principles. First, about Norman equation, generalization Schrödinger equation, deterministic. And second, the initial projection hypothesis, or IPH. At a temporal boundary universe, the density matrix of the universe must be the normalized projection onto the subspace, a low-dimensional subspace with a total Hilbert space. Here, both H hat and HPH are left open-ended. This we don't quite, I speed up, sorry, thank you. This we haven't quite figured out yet, and we're trying to get clear on what H hat is. And HPH is somewhat fuzzy, even given the macro variables. So there's a different way to think about this on this picture that will be not so obvious by reading this, but given the context, it includes a definition of what HPH is. Okay, there is no accompanying statistical postulate because there's only one nomologically possible initial quantum state. To solve the measurement problem, we have the three ways: Bohmian Wentaculus, averaging Wentaculus, and GRW Wentaculus. So add this to Bohm, we have Bohmian Wentaculus. So everything is the same, but postulated quantum state at T0 is this one. Okay, and add this to average, we have averaging Wentaculus. You have other choices too. And you can add this to GRW. It's indeterministic, but still constrain the initial quantum state to be this one. What differences does the Wentaculus make? There's a lot, as I already do. I only have 5 minutes left, so I'm going to be quick. Initial quantum state, status with path hypothesis, nominal vagueness, unification, probability monism, strong determinism, and I can go on forever talking about this. So in the Wentaculus, initial quantum state is sufficiently simple. If the path hypothesis, say, is sufficiently simple to be a law, then the projection, normalized projection onto the path of the subspace is sufficiently simple. Then informationally, they're going to carry out the same information. There's not more information in the density matrix than the path of the subspace itself. And this supports interpretation about the nature of quantum state, that the Wentaculus initial state can be nomological. And this is most natural on the Bohmian Wentaculus, also possible average and less natural in GRW, but still it is possible. What does it mean for something to be nomological? Here's what I mean. The Hamiltonian function in classical mechanics is nomological. We have equations and we have function. I'm thinking not just a symbol here, okay? Thinking spell out what is H function. Graph, potential, electric potential, all these potentials in function, still simple closed function. And you do all these derivatives and get velocity field on phase space. What are the marks of nomic for the H? Well, it is H generates motion. It's like an engine generating velocity field. H is simple. And on one way of thinking, H is fixed by the theory. Give a different H, you have different theory, different system. And no more logic necessary. Interpretation here is that H is not ontological as a field on phase space or something, but nomological as a law or part of the law description of the equation. To kind of thinking about Hamiltonian equation as specifying also some particular H. That's one version of the equation motion. In contrast to Maudlin and Untitled, which are taking on complicated values, not generating motion, or not completely fixed by the theory, and then nomologic contingent. So for concreteness, focus on the Bohmian version of Wentaculus. You can write down a similar kind of equation motion in terms of the initial density matrix with time evolution operators, position representation, gradient. Okay. Does W0 now have the marks of a nomen? I say yes. This is part of the generator of motion, and W0 is simple. W0 is fixed by the theory and nomologic necessary. And this is how I understand Bohmian-Wentaculus equation motion. And this encodes the guidance equation, the von Neumann equation, and initial projection hypothesis in one equation. That's how I'm thinking about this way of thinking of the nomological view of the quantum state. So similar to the Hamiltonian function in the previous equation motion. So proposal here, W0 can be thought of as nomological on Power's laws of nature. Okay, so it's good news for being a real quantum state. Say more about this. You can do the same thing on GFW. And it's not always available for standard versions that take psi to be the Jet quantum state. The simplicity of particular vector psi 0 in any subspace is not guaranteed by the subspace simplicity itself. Maybe some other route is possible. With a duet equation or other version of quantum gravity, maybe they'll deliver the same result. But this, the Wentaculus gets it in a way that is, less speculative. We can see how it gets it by the quantum state being simple. So it's kind of reliant on the past hypothesis being simple, which is something we have independent arguments, independent considerations. I mean, it's not completely non-controversial. Okay. IPH. Maybe I should speed up or.
Well, we won't have time for discussion.
Good point.
Well, I mean, we do have time. This dinner's until 6:45.
Okay.
Maybe finish in 5 minutes.
Okay, I'll talk really fast. Okay, so the initial projection hypothesis directly involved in dynamics. As we have seen, we rewrite the methodological terms of function specifying IPH. Remove certain words that pH is not law-like. It's good news for fundamental Nomi status of low HB initial condition. Okay. Nomi vagueness is that IPH is exact, but traceable. So this removes my worry about the dilemma between Nomi vagueness and this untraceable version of arbitrariness. It's not that in the Wentaculus cannot have this precise past hypothesis on the gamma zero law. It's that when you do that, you're kind of like on two horses of a dilemma. You have to embrace a version of arbitrariness I find problematic. But this is you can stipulate there's going to be a precise boundary, subspace in Hilbert space, that's the HPH. And this will be traceable because of the IPH. Because that this initial density matrix will be involved in dynamics, giving you, say, the velocity field of quantum mechanics, or the time multiverse, or the probability distribution for GFW histories. So this has a dynamical effect, unlike the case of the boundary of the past hypothesis. The boundary of the subspace here will kind of basically correspond to what the ontology is. Okay. So I'll say more about this in this article. Dynamical unity. In Bohm, there's actually something I found interesting, and I didn't really understand before, is that if you have spin Bohm mechanics, you can waveform version, you're not going to plug in, say, system 1, system 2 in the universe, and they're interacting and so on. System 1, conditional wave function. Plug in what? Plug in the configuration of the environment, but there's no actual spin to plug in for particle 2. So what you do is not to write down the spin indices for the conditional wave function for system 1. That's not going to be in the Hilbert space system 1. It's going to be contracting the spin index, like summing over spin index, like averaging. And that's going to give you a density matrix. This is how Adlam and co-authors define the conditional density matrix for the psi version of Bohm mechanics. In this, you sum over the spin indices of the second particle. We just do this, plug in the configuration of the second particle. Second system, and then you get a conditional density matrix, even for pure state case normalization. So even if a universe is in pure state, the configuration of the most subsystems are guided by the mixed states according to the W Bohm mechanics dynamical equation. So you're already using W Bohm mechanics in the subspace systems inside. So in this way, the Wentaculus is going to give you more dynamical unity. The universe and subsystem are going to get the same kind of laws. Okay, not going to talk about GLW ever here. Probabilism gone. There's no need for probability distribution over initial quantum states. There's only one possible choice. The only fundamental probability distribution is the quantum mechanical one. The probability map, the Wentaculus probability map, the Wentaculus probability map is entirely based on quantum probabilities. There's no extra probabilities in terms of initial possible quantum states. And it's good news for theoretical economy. Okay. For aberrations, I heard this talk on Sunday already. Okay. Let me skip. Generalizations. You don't have to use pH. There are other versions such that you can still use something like pH, determining what we can choose the nationalist matrix. So pH is a simple principle. There can be other principles that are similar and simple. So, and that can be generalizing the Wentaculus idea, start from the full Hilbert space, and then show using simple principles, if there are any, to determine initial subspace, H0 in H, and to the next quantum state in the subspace, the normalized projection operator onto the subspace. And the natural choice would be always simple and unique. I think Don Page has something like this in mind when he was thinking about one version of quantum cosmology. Okay. So disadvantages of the Wentaculus and realism goes against some bit of conventional wisdom. Not exactly, but I mean, but if it's gnomic, then we lose time transition invariance, dynamical laws, maybe skeptical worries, partial state space, cosmic analog. I say more about this in the paper version. Okay. And these two are in response to David's words. Okay. Weighing the pros and cons. Okay, I might be biased, but I'm thinking on the Wentaculus is on the right side or the left side. Okay. All right. Skip. Okay. Density dimension realism is, I think, theoretically fruitful position. In this talk, we've shown its advantages using the Wentaculus regarding the following aspects. Then we should explore. I invite you to consider the pros and cons of the Wentaculus. Whether the universe quantum state is pure or mixed is an open question. It can make a significant difference to how we understand the physical world and physical laws, physical probabilities, and so on. If the Wentaculus is true, then laws will determine not only time evolution, but also initial quantum state. The possibilities actualized by the initial projection hypothesis. All right, here's some papers. Thank you for your time.
So let's have some discussion for at least 15 minutes. So, see you first.
So it's somewhat elementary question. So how do we know that so the past hypothesis typically is chosen not just only for its low entropy nature, but also to make sure that it's consistent with everything that we know about the world. The set of quantum states that would satisfy that, why should it have the structure? Why should it have a linear structure? It's not obvious to me that it would be a subspace. Why should? Can you say a bit about that?
About dynamic evolution?
No,
In the Hilbert space.
yeah, the subspace, what you are calling HDH, right? It's a subspace, so
Yeah. It's stronger than,
a
collection of
subset.
very
Yeah.
So it is something that might be, stringent, but it is standard in quantum system mechanics. It's a postulate, right? So the idea is that you can have orthogonal composition of the Hilbert space into subspaces, and they represent what we usually might call the macro states of the system. And there are going to be some fuzziness in the boundaries. So if you have all fuzziness, it might not actually look like a subspace anymore. But given some idealization and say for simplicity, we'll consider just the subspaces as candidates representing the macro space. But this is something that,
I think in the statistical mechanical case, usually the point is that you want a certain observable to have a certain expectation of it. And that gives you subspace structure because then you can take linear combinations and that will preserve the expectation of it. But as far as I understand in the past hypothesis, there isn't a quantum mechanical, maybe there is, I'm not sure, but it's not obvious to me that there is a well-defined quantum mechanical observable which you want to take a certain value.
for the universe as a whole.
In the initial condition of the universe.
Yeah, it's a good question. So Ashley Power and co-author, they're trying to actually work on this topic. to try and find observable, giving you the class and the ball of wave functions. They have nice properties. And it's simple quantum cosmology models with simplification, reduction of many dimensions. But yeah, there's no guarantee, right? The density of the universe will have this nice structure being the projection from some space. I think that's definitely a good worry. But I think it's something like simplistic considerations that drive us to this particular nice state. If it's false, then good. If it's true, then that's kind of like the super virtues being true conducive. That's like something we do for other dynamics too. Why, right? Why should all the past observations that we haven't done obey exactly the same kind of situation? We have analyzed many experiments, and they seem to confirm certain theories, and they're simple, but there's no reason that the universe can be described by a complicated model.
Okay, I have follow-up questions, but
Okay.
maybe we can have others.
Yeah, that's a good question. Thank you.
So, Eddie, there's a tension, I'm not quite sure I understand, there's a tension between what you presented here and what's normally meant, as I understand it, by the suggestion that the wave function could be known. What Shelley has in mind, coming kind of back from the Wheeler-DeWitt equation, Wheeler-DeWitt equation sort of suggests maybe if you bring general relativity into the whole mess, that the universal wave function will actually be stationary. Now, first of all, I take it from your point of view, that would screw everything up, because if you put then a condition of low entropy at one end, you've got a low entropy forever, right? I mean, it's always low entropy.
Right.
So you can't have that in mind. I guess you have in mind that there's some initial low entropy condition that's kind of simple, and maybe you're arguing here unique. But in a Bohmian situation, of course, the initial condition is not just the initial quantum state, whatever it is, but also the initial configuration.
Yeah.
And of course, because it's a deterministic theory, you would really worry that if there was something really nailing down in the Bohmian situation, some simple, unique configuration, then you would never get a complex world.
Right. I don't
Right, the
think,
simplicity would kill you.
yeah, I don't think there's going to be, I don't have a candidate for a simple configuration.
Okay, so you really still probably have a probability distribution that's going to represent the possible initial configurations.
Yeah, that's going to be part of the Wentaculus for Bohm. So it's going to look like you have the unique quantum history, but non-unique Bohmian projections.
Okay, so that's, anyway, that version of it does not lead you to strong determinants.
No.
Okay, that's all I wanted to.
Yeah, strong determinants don't apply to everything.
Verify that that's correct.
So the average Wentaculus is only one of the three. That's only deterministic. Maybe that's bad, maybe it's a good thing. Yeah.
Just trying to understand.
Yeah. Okay. Thanks.
Yeah, just a thought about that. I mean, I don't know if a stationary universal wave function is, the end of the world for your view, right? Because I would have thought that if the wave function were stationary, then the right way to define your initial state would be to use something like a K-torsions formalism and say, the initial state relative to a clock reading time t equals 0 has this form, and then there's this simple state. And then, I don't know, you have to think of the details, but I would have thought you could still have the same kind of picture with it sort of past that. But it would be a mixed state, right? Because the time is pretty different anyway. So it seems possible to achieve that even within a stationary sort of overall.
Oh, interesting. Yeah, that's good. So maybe here's something that I can consider, which is something I talked about in the paper for the volume integration data algorithm and the Chancellor published this year, which is that the Bohmian quantum mechanics don't have more different freedom. We have quantum state and configuration. You can define the Bohmian entropy as something more than the quantum entropy of the quantum state. It's like conditionalized on the effective or conditional quantum state of the system, effective quantum state. They can still have non-trivial dynamics even when the whole thing is stationary. That's one reason they can think they can solve problem time even when the quantum state is stationary. So maybe in that case you have initial configuration constrained by initial density matrix for distribution and evolve, and then particle will carry very well complexity over time.
Yeah, because you could have this non-trivial density matrix, like relative to t equals 0, you could have different state set relative to different times, and as the paper just goes, you get this.
Yeah, maybe that's maybe another version of the papers. We understand better. Yeah, thank you.
I think I get the picture for Bohemian mechanics, those who work. But you seem to suggest that there's a Wentaculus version for Everettian.
Yeah.
So what's the ontology?
Is going to be whatever that Everettian might like. So
We don't have the answer to that.
the Everettians might going to say, okay, I can get everything from a quantum state. Then they're going to say, I can get everything from the density matrix of the universe.
So this law,
Well, for them, it's not be a law. So if they want to, for this to be a law, there should be a primitive ontologist kind of version, like SM. So Lorry and this version of Schrödinger's first theory plus mass density. So average plus mass density deterministically from the quantum state. You have a density matrix version of that with the mass density. That is what's fundamental and material. In the law, we involve the Wentaculus. Because the ontology still be a four-dimensional field.
another law question I have. If you thought the ontology, let's say, was particles, and the universe consisted of particle positions, then it sounded like you were saying, I think you were saying this, that the Wentaculus could be thought of as systematizing the whole history of those particle positions.
Yeah.
The language in which the Wentaculus that was stated is not the language of particle positions.
It is. It is.
Well, it's there are many defined things. It's very complicated.
Well, you mean like Hilbert space?
Yeah.
Ah, interesting. I was thinking the Hamiltonian.
The Hamiltonian too would be very complicated. I mean,
In
I
terms of
think,
position.
I'm not saying this is an objection anyway.
Right.
I'm just wondering exactly, well, you could think about this relative to, let's say, I mean, now sort of the Lewisian picture of things look awfully simple-minded for many reasons, but imagine, I mean, you would want the,
Well, I was thinking that even for that person, you might take this to be the true law, whereas the dq over dt, particle velocities, in terms of some functions on R6n actually can be in R6n that give you a velocity field. But this function can be characterized as simple insofar as this, and this can be characterized mathematically in some ways equivalent in this position representation. So here I'm giving the operator formalism, go to position representation, take a gradient, and get me the velocity field. But you can think of the whole thing being done in position representation should be equivalent to simple too. There's a nice translation.
put just in the language of particle positions in time,
Right.
you'll get something, you'll get that, and you'll be able to characterize.
Yeah, it's like Hamiltonian classical mechanics. You have,
I see how it works in classical mechanics.
right. So that's the picture. I think one can insist on this. Suppose you have perfect atoms into the cubes and geometry on configurations.
Last question I have in mind is, you suggest along the way something about empirical, that this would be empirical, various things would be empirical equivalents. Whether you took the Wentaculus, or the Wentaculus quantum mechanics together with the Wentaculus.
Right.
And so on. They're empirically equivalent. Are they equivalent in stronger ways? Also, is there some way of saying that these are two different universes that you're describing, two different possible realities?
Oh, I see. They have different trajectory particles.
So the particles would be different.
In general.
So the particles would, that's right, okay. So these would really be saying something different about what these fields are like,
Physically.
even though with respect to any measurements that were imagined.
So for,
I see that.
yeah, they're physically inequivalent but empirically equivalent.
Right, so that's a very nice example.
So it's in a general case for any quantum theory, or maybe even a general class of theories that do this.
So this is bringing up, I mean, you and I have had many hours of conversation over the years about this, and most of the worries I've brought up are too detailed to let, you've had to go through things very fast here. So I don't want to bring up details, but maybe there are two things worth mentioning. One is on this question that we've discussed a lot about empirical equivalence,
Right.
okay? The sense of empirical equivalence, the sense of the argument for empirical equivalence that I'm familiar with in discussions of these theories is an argument which I think is quite straightforward and quite clear, that that the Wentaculus is going to give you the same probabilities of configurations as a function of time as the Mentaculus does. The naive quantum Mentaculus does. There is a question which we've discussed a lot and which I don't yet know the answer to, but maybe there have been more developments about whether that's all one wants from empirical equivalence. So say both of them say that there's a certain probability that at this time the configuration of particles in my brain is going to be such that I'm thinking I'm sitting here in a classroom and talking to you and blah, blah, blah. But as you said just a minute ago to Barry, the trajectories, of course, are going to be different. Now, we're familiar with different guidance conditions in Bohmian mechanics, which give us different trajectories, but the same probabilities at a given time. But they give us more than that, okay? They not only give us the same probabilities at a given time, but we can make arguments that, as it were, they give us the same probabilities for macro histories of configurations, or something like that. So that not only is the probability of my sitting here thinking I'm in the room correct, but there's also a high probability that my memories of how I got to this room are actually correct, and so on and so forth. So I think it would be a pretty minimal notion of empirical equivalence just to show that the probabilities of configurations as a function of time match with the Wentaculus ones. We think that the Wentaculus ones give us a story about the history of the world, which is macroscopically speaking, I don't know what the right requirement is, but in some sense, what we think, okay? Not only am I sitting here with certain probabilities, with memories of having conducted certain experiments with certain probabilities of their outcomes, but I actually did, with high probability, conduct the experiments that I thought I conducted, and so on and so forth. And what would be helpful for me is to see, first of all, there's some sense in which I don't even know exactly what I'm asking for, okay? Right, but what would be helpful for me is for you to tell me back, here's what I think you're asking for, and here's how I can give it to you in the Wentaculus.
I appreciate the worry in the question, and this is something I call the dejection from potential mismatch of records. Right? Say record is saying it is moving, but it's not moving. That's bad. Or suppose I say I remember this, but it's not. Didn't happen. That's bad.
Right.
And this every question mark kind of worry. Is it like that? Was continuous or solid? Question mark. Yeah, jump over the road.
Right.
Okay. So there's something here. I think we can make progress. Not all the way to proving macro history equivalence. We'll probably do that because.
I mean, maybe, I'm not sure, macro history equivalence was sort of a very crude first pass on what I think we need. I don't know exactly what
the precise version of it, I think, will be hard to establish rigorously, even for satisfaction for the wave function version. Like, what is the right macro history, given the passive hypothesis plus Schrodinger equation? Do we have proof? We have plausibility conjectures and so on. And if they have different macro histories, which one is correct? And they're so close. So even if they're inequivalent in this deeper sense, maybe the one text is right. And this is, I mean, I'm not saying that.
Presumably, if it's the case in any theory, okay, that that our memories turn out to be wildly false and so on and so forth, even if it's getting the right configuration. Then then especially if there are other theories where they're less wildly false, that's going to be a big check against.
I think it's a good check. So we're going to kind of see the cases like this. You propose one case. I think it's similar to the one that discussed earlier with Tim and Barry, for moment lighting states. So in the paper version, I have a short response. There's non-paper writing, which is the conditional density matrix and collapses of the conditional density matrix. I think I've seen a graph of this, which is a response more than the form, which is to say that in a specific case of potential mismatch, it doesn't actually happen. Once you have the density matrix understood in this way, then you see that there is going to be an effective collapse. The Bohmian one-packet density matrix obeying Maudlin equation, because the coherence and measurement instrument records is going to induce this discontinuous collapse of the conditional density matrix. That's going to be the same as in Bohm mechanics, like Einstein's question for Bohm, single particle, the stationary wave function. Bohm says, well, if you measure this, it's going to move again. And that's going to be the same situation there. I think that while we can make progress in this, maybe not completely satisfactory, but just can make progress to see how collapses work.
I think that sounds like the right direction to go.
Yeah, I think that the collapses can generalize in this way.
That sounds like the right direction to thinking. Good. Can I ask 2 more short questions, Barry?
Sure.
There's 2 minutes.
Oh, okay, so maybe I should stop. Okay. Well, if no, does anybody else have a question? I can ask one.
Just before you leave David, that maybe this is, I don't know if I understand David, this is a time inverse version of it. When you say that this is at the universe level and not at the subsystem level, I want to understand your concern. Is it that you feel like this is what people are doing now already at the subsystem level, and you want to say, well, we should be doing it at the universe level? Or do you think there's specific problems in bringing this down to the subsystem level? In other words, if I'm preparing an experiment, what does it mean to prepare it in a density matrix?
Oh, that's not what I mean. That's not motivation. It is one possible motivation, it's not mine. I'm not too worried about operationally how to prepare states and how to associate states. We can associate them with pure states, mixed states. This doesn't carry ontological significance yet. It's only when at the level of the universe as a whole, dynamics of the universe, and we see that the cry for explanation or interpretation is different from standard one we have. And maybe there's room for 2 different interpretations for the same practice we do. And one reason for equivalence here is that, well, there's no difference whether quantum state universe is pure or mixed. On Wentaculus or Wentaculus. We're going to do the signs the same way. We're going to do associated wave function in this case, which could be equivalent to a density of pure state density matrix. Or we don't know whether we have a distribution of quantum wave functions for the subsystem. That can be understood in different ways too. I think there's a wide kind of spectrum of possible views you can take on the subsystem states that is kind of independent from what we take for the universal state. So the thesis about density matrix realism should be called universal density matrix realism. I can also take subsystem matrix realism is not the view I want to focus on, but something that people have defended, like other people.
Emily goes, we have enough time, because the restaurant is really only.
How you doing?
Diego, I said, on his birthday, Ken, Bishop, you can come to dinner, right? Excuse me, Bishop. You're really excited to come to dinner, right? Yeah. Great. So it's, you see, Eddy.
I know that but I don't think I was.
Yeah.
I don't think anybody was there.
Yeah, you put down Saturday.
How are you? I'm doing well.
You in?
Some of this.
Something else was coming with you. So the exercise. So.
I'm Start. I'm a graduate student at HBS. Yeah, I was also one who said it was a generous format, but I guess it's.
Oh, I think, so you could come.
Yeah,
I think it's based on you.
Yeah, that's-
I think we got people going now, so I will call them and say.
I just started, yeah. Yeah, I'd be happy to stay for my work.
Thanks for sending it. And I'll send it around.
Yes, we're meeting Thursday for lunch.
Just waiting for possible. So, yeah.
Okay, awesome. Can I ask you, so will you be okay if I leave my suitcase at your place on Thursday and pick up later?
Why don't we do something? Thursday night, that's why please.
I think you mentioned to me earlier Monday
Where should we start? Yeah, you know, where should we start? Yeah, I don't know. Because I know that's a great resolution, it's a 6. Yeah, who did that?
That's what makes it.
Yeah, sounds good.
I have passed.
Go ahead, what are you asking me?
When is the talk starting? The exact time at which the talk is starting?
It will start at half past.
Yes, okay.
You can do something to make that happen.
Yeah, my schedule is really open on Thursday, just whenever that works for you.
Okay. I probably do one more, but it's a little hard because I don't have to.
Yeah, sure, maybe I'll just send you.
Wait.
Yeah.
On the way to.
Okay. It's a.
Oh, yeah.
Okay. So which we would need for the meeting. So why don't you pretend right now that you come to my place at 1 o'clock?
Sounds
But we should be able to do once we figure out what Joe is doing. Just a few minutes, just to keep it. You don't have it?
Yes.
But I do.
Okay, also, I don't have to, we don't have to eat, I understand there was Yeah, sure, I can just be in the neighborhood. I just want to ask if it's okay if I leave the suitcase with you and pick up later at night? Oh, yeah, I'll just leave it at home.
Earlier, just bring it there. If you're gonna do it.
Yeah, I would just leave it at home and probably easier not to carry all the way downstairs.
Exactly, very odd.
Yeah. Okay, awesome, thank you so much. Okay,
So it's easy to go fast, but it's dangerous, it's just not safe.
That's what I want.
Just study for 3 minutes, almost because it's not
Barrier. So we'll screw you up if I can't do that.
I don't know, this would be, it might make a confound.
Because
Right now,
if it doesn't, if it's
I
not a
could call them
problem,
right
if
now.
it's a problem, it's okay.
Call them right now, so I can call.
I mean, is it's important for your review to be extended or just a?
It's important not to put weight on it. That's the issue.
Because I keep seeing people which, you know, didn't exist when I was young, who have passed on and so on and have these little like scooter things. And they just rest the thing and they roll with
But
it.
that's mainly the students for the angles. They're taking it from the angles. They're not taking the pressure off. It might be.
I terrible at what, as what the city council is possible, or is it reviewed by
This
the
is
council?
all schools. I could not get this operation, and then I would need a knee replacement. Be able to find all right. I'll never need a knee. But I can tell you the joke. The joke.
Okay.
Right. Also, just, I mean, but I think it's kind of like, it doesn't quite capture just to point out that it's not high translation invariance isn't something of any value in and of itself. I feel the same way about the term. It's not something right, that is, here's what's true on this though. The rules connecting outcomes of experiments at one time and outcomes of experiments at another time are not going to depend on the time. They're only going to be able to one. Right. No, good. But so that's right. So that's what I mean by sort of at odds with itself. It's the same way I feel about determinism. Determinism isn't of any value in and of itself. But if the connection between outcomes of experiments, if there's a deterministic rule connecting, but the theory in some way, given its ontology, denies this, even though it doesn't deny it. But it denies it.
And then we spend a half hour to get her to straighten them out.
Time to start the talk.
Okay, we can start again. Okay, next speaker is Emily from the Rockland Institute in Western Ontario. And I made her a quick, very interesting talk she gave on Jacob. I said, I thought Jacob was going to be here.
No, I think we had to go back to Thomas.
Anyways, okay, anyhow, it was a really interesting talk, and since we're going to do this, and she's going to be in New York, this is very promising, she's our next speaker.
Hi everyone, it's great to be here. Thank you so much for the invitation. So what I'd like to talk about today is this age-old question of why we can't change the past, or at least why it appears to us that we can change the future and not the past. And so what I'd like to do today is present an approach to this question which is quite different to the sort of standard thermodynamical approach, which I see arising out of a sort of interesting new research program in Wentaculus Foundations called the process matrix formalism. And so despite the slightly combative title of this talk, I don't actually think these approaches are necessarily in competition. I think they're potentially very complementary, and there's room for some interesting interplay between these two approaches. So I'm interested in thinking more about how what I'm about to present relates to the more sort of well-known approaches in terms of the Wentaculus and counterfactuals and so on. And of course, obviously, this is the right place to talk about that. So if anyone has thoughts about how those things fit together, I'd love to hear what you have to say about that and any questions. So basically, I'm going to begin by making some comments about the sort of standard thermodynamical approach, and in particular raising some questions that one might naturally have about it. I'll then look at a more specific question relating to closed causal loops. I'll then introduce a sort of process-based formalism that I'm going to use to discuss this question and use that to motivate the need for what I call temporal interdicts. I'll then introduce the process matrix formalism and describe what the process matrix formalism tells us about temporal interdicts. And then finally, I will talk about some consequences of this approach for causation and indeterminism. So what I call the standard account is, roughly speaking, the idea that the temporal asymmetry of influences is going to do with thermodynamics, to do with the increase of entropy. So this has been presented in various ways in the literature, but I guess all of us here are particularly familiar with the Wentaculus approach, which has which we'll all know quite well, so I won't describe it in detail, but here's Professor Elbert telling us that the temporal asymmetry of influence is to do with the difference between the number of routes we have available to us to influence the future versus the past, which is supposed to be a function of the increase of entropy, roughly speaking. So a question that some people initially have about this approach is that it sort of seems that as if the temporal asymmetry of influence is a consequence of the increase of entropy, then it must to some degree be sort of statistical and approximate, because the increase of entropy itself is statistical and approximate. That is, it would sort of seem on that perspective here that it's not completely impossible for me to change the past, it's just sort of very unlikely, which sort of seems to indicate that if I tried enough times, I would eventually succeed in changing the past. Of course, realistically, I would probably have to try many more times than I could possibly achieve within the course of my actual lifetime. So this is not sort of a immediate practical problem, but it still seems a bit odd conceptually, because at least intuitively, it does feel that our inability to change the past isn't approximate in any way. It's a sort of very unforgiving, rock-solid barrier that the past is fixed and we can't do anything to change it. So there's sort of questions you might have about how the approximateness of the increase in entropy is to be reconciled with the intuition we have that the past is totally unchangeable. So one way one might consider addressing this question would be to say, okay, maybe it is in principle occasionally possible for us to change the past, but because changing the past is associated with entropy decreasing behavior, what that means is that we won't ever remember changing the past when we succeed in doing it. And that could explain the source of the intuition we have that the past is unchangeable, because whenever we do succeed in changing the past, we don't remember it, and thus we have sort of this false impression that the past is completely unchangeable. But there's still something a little bit odd about that account, because at least for me personally, my impression that I changed the past, that I can't change the past, isn't just based on the fact that I have no memories of successfully changing the past. It's also based on the fact that I just have no idea whatsoever what kind of action I could possibly take to have some influence on the past. I don't know what kind of action could have even a small probability of influencing the past. It seems to me that my actions, sort of at a conceptual level, can only have consequences in the future. And I guess there's an argument one might make to the effect that, in fact, there are processes available which change the past, but we just never remember anything about those processes, and so we just don't know about them, we don't have them included in our physics or in our sort of conceptual model of the world. And that is perfectly logically possible, but I find it a bit unappealing, because it seems to involve postulating this whole realm of unknowable processes or unknowable physics that we can just never find out about, because we can never remember anything about them. And sure, the world could be that way, but it would be nice if perhaps we could find this feature of our reality emerging out of standard physics without having to sort of imagine this unobservable realm of physics that we can't access. So here's a slightly more detailed version of this concern. Let's suppose for a moment that there is some process P2 which can be used to influence the past. So P2 is a process such that I put an input into it at the present time, and it produces an output depending on my input somewhere in the past. So we'll suppose for the moment that P2 may be very difficult to implement, that is, I may implement it only with very low probability of success, but that when I do succeed in implementing it, it is deterministic, so it always produces the same kind of function of the input. So now we can imagine producing a kind of composition as shown here. Basically, in this picture, my past self takes the value of some bit A and uses that bit as the input to some deterministic process P1, which produces an output somewhere in the future, the output being a function if P1 of A. My future self takes that output and then uses it as the input into process P2, and process P2 then produces its output somewhere in the past, and we can arrange things such that the output of process P2 appears in the past just before my past self chooses the input into process P1, so my past self can apply some function g and then use the output of all of that as the input into the original function. So since P1 and P2 are deterministic, we can choose the function g such that we can be confident that the initial value of that bit a is not equal to function g acting on the output of P2 acting on the output of P1 acting on a. So it looks a little bit like we're going to end up with something like a logical contradiction, right? This input bit a seems to have two different values at the same time. So for example, if we imagine that both of these processes P1 and P2 are just identity channels, so they produce an output equal to their input, and if we choose G to be a bit flip operation, then this input to P1 here is going to have value 0 and value 1 at the same time, and that seems like a thing that probably can't occur, right? We can't have situations in which the one and the same variable has two different values at exactly the same space-time point. So at least naively, this seems like some kind of logical contradiction. And so it seems like this sort of thing just can't occur. Moreover, it seems like it's not enough that this should just occur with very low probability. It really needs to be the case that this just can't occur at all, because presumably the universe can't contain even one logical contradiction. Moreover, at least on the kind of fairly realist picture of the world that I tend to adopt, it seems like it's not enough that nobody would remember this happening, right? If there's a logical contradiction, then there is a logical contradiction, regardless of whether anybody observes this, remembers it, or anything like that. And so, closed causal loops of this kind need to be completely impossible, regardless of whether anybody can remember them happening. So I'm now going to use that kind of idea to motivate a slightly different way of thinking about the temporal asymmetry of influence. I'm going to do that by trying to characterize what these kinds of consistency issues have to tell us about what modal structure has to look like. That I think seems sensible because, on some level it's clear that a temporal asymmetry of influence is a fact about modal structure, right? It's about the fact that I can or think I can influence things in the past, and I can't or think I can't, I can influence things in the future, and I can't influence things in the past, or at least so it seems to me. But in this talk, I'm not going to say anything very specific about how you should think about modal structure. You are welcome to be some kind of primitivist about it, or to be a Humean about it, or whatever takes your fancy. But what I will say is that however you think about modal structure, it seems fairly reasonable to say that modal structure should be defined in such a way that it doesn't give rise to contradictions. That is to say, regardless of whether you think modal structure in some sense brings about or creates the non-modal facts, or whether you think the modal structure is in some sense just a systematization of the non-modal facts, given that we all think, most of us probably think that the non-modal facts cannot contain logical contradictions, it seems as though the modal structure should also be constructed so as to prevent it giving rise to logical contradictions. That point is somewhat like Novikov's self-consistency condition, which was a condition he applied particularly to study processes in closed causal loops or closed time-like curves, where he sort of noted this requirement that the non-modal facts do not contain contradictions. Here, however, I'm sort of applying this at a slightly higher level. So rather than applying the consistency condition to the non-modal facts, I'm asking what consequences the requirement of non-contradiction in the non-modal facts is going to have for the way you define modal structure. In the rest of this talk, I'm going to largely characterize modal structure in terms of processes. I will understand a process to be a family of possible experiments characterized by certain kinds of regularities. So that is, a process is understood to produce certain kinds of stable statistical regularities, and so the process is in some sense defined by the probabilities for outcomes that we expect to see, conditional on choices of inputs. The reason I'm doing that is because that is how processes are defined in the process matrix formalism, so that will allow us to connect all of this up with that research program in a nice way. So, the requirement that modal structure should not give rise to contradictions means that we're going to have to use something that John Bell calls temporal interdicts. This is not that John Bell, it is a different John Bell. But what the other John Bell has to say is that temporal interdicts are required to block changes of the past in order to avoid having logical contradictions. And Bell sort of seems to be suggesting that temporal interdicts, in some sense, have a higher level of modal or nomic force than ordinary laws of nature. Perhaps we should think of them as something a bit like Long's meta laws, but they're in some sense more necessary than the ordinary laws of nature, because we can sort of at least conceive of the laws of nature being broken, but we can't really conceive of there being logical contradictions in the universe, or at least if we can conceive of them as still less conceivable in some sense than the ordinary laws of nature being broken. So in some sense, it's quite important that our modal structure should have some kind of temporal interdict in it. And there are a number of ways in which we can enforce temporal interdicts to avoid changes to the past or logical contradictions. One possibility is just to define our modal structure in such a way that there just aren't any processes which could ever give rise to contradictions. So just limit the set of processes available to be chained together such that no matter what anybody does, or no matter how they end up being composed in the course of the evolution of the world, or the non-evolution of the world, if you choose a block universe picture, no matter how those processes are joined together, there's just nothing anyone can do to make them cause a contradiction. An alternative is to say the modal structure does contain processes which could, sort of mathematically speaking, give rise to contradictions, but as a matter of fact, whenever anybody tries to create one of those contradictions, or whenever one of those compositions is going to happen in sort of the course of natural happenings, the universe arranges some kind of accident or interferes with people's free will in such a way that contradictions like that never actually occur. So that is the kind of suggestion that's often made in discussions of things like the grandfather paradox, the thought being that we can avoid the grandfather paradox if the time traveler just always has a terrible accident before they are about to kill their grandfather. So that would be another way of ensuring that we have consistency. A third possibility would be to allow contradictions to occur, that is, allow that one and the same variable can in fact have two different values at the same space-time point, but just have the universe branch so that our two values just go off into different branches of the universe, and so we're still safe from contradictions because those two values are at the same space-time point, but they're in different branches, so everybody's happy. Now, I am not very fond of branching universe approaches, so for the purpose of this talk, I'm just going to disregard option 3, so that leaves us with options 1 and 2. Both of these, I think, are perfectly logically possible, but just as a purely sort of empirical observation, it seems to me that what our universe has chosen to implement is option 1. That's because, in my experience, we don't often find ourselves trying to create certain kinds of compositions and then just having accidents or suddenly changing our minds. What appears to be the case is that we're limited in the processes we have available to us, such that there just aren't any processes which one could compose in such a way to create contradictions. And indeed, I don't know any processes that I could compose to create contradictions, so at least looking at the status of our current science, it seems true to say that in the regimes we have so far accessed, the processes available to us are not processes which give rise to contradictions. So it seems natural to ask then, what does that requirement entail for the modal structure of our universe? That is to say, what kinds of processes are possible if we eliminate all processes which could possibly give rise to contradictions? And I've been thinking about this question for a while before I discovered the process matrix formalism, and I was really excited to discover that this is basically exactly the question that process matrix people are trying to address. So they don't perhaps describe what they're doing in exactly those terms, but when you look at the structure of what they're trying to achieve, it's clear that is essentially the question that they are addressing. So in the process matrix formalism, the idea is to describe and characterize possible processes in a very general way. In particular, we are not going to insist that the processes are implemented against some sort of fixed space-time background or inside some pre-existing causal structure, and we're not going to require that the processes having any known implementation in current physics. So to do that, what we do is imagine that we have a set of laboratories where agents can perform local operations. Usually we say that the operations include all operations allowed by quantum mechanics locally. And then we use a process matrix to encode the set of all possible dynamics between the labs. And that process matrix is defined in a very general way that doesn't assume any particular ordering of the labs or any particular causal structure or any prior assumptions on how the labs can be connected together. So it allows us to implement a variety of dynamics that are not permitted by sort of known physics, such as dynamics going around in loops and so on. So the only requirement really that we place on the dynamics is that we insist that these dynamics do not give rise to logical contradictions. So the process matrix formalism has a particular mathematical definition, and you can prove that if the process matrix satisfies this definition, then indeed no possible choice of the local operations by the agents in the laboratories will ever produce a logical contradiction. So that rules out certain sorts of processes that you might imagine. So in particular, the example we looked at earlier, which was essentially just the identity channel around a closed loop. That process is not possible in the process matrix formalism because if the agent at the bottom chooses a bit flip operation, that will give rise to a logical contradiction. So the way that the formalism is defined means that the process matrix formalism essentially circumscribes exactly the set of processes which can be possible if we insist that the modal structure doesn't allow the creation of logical contradictions. Now we can also use this formalism to define some more specific sets of processes. For example, we can define causally ordered process matrices, which are compatible with the existence of some strict partial order, such that the probabilities for the outcome obtained in some laboratory depend only on the settings in the experiment which succeeded in the partial order. And we can also define causal processes, which are a bit like causally ordered processes, but slightly more general, in that we allow probabilistic decompositions of different causal processes. And we also allow that in some cases, the choice of order for laboratories later in the process could depend on inputs to laboratories or laboratories earlier in the process. So the point of making this definition is that we can now make the empirical observation that so far as we know, in all the regimes we have so far looked at, all processes known to occur in reality are causal. And moreover, the strict partial order used in the definition of the causal process matrix is just temporal order. So I emphasize that the process matrix formalism is not defined inside a fixed sort of temporal order, but we see something like temporal order kind of emerging from the definition of various kinds of processes. Certain kind of processes just have a sort of natural order built into them, and when we look at how those appear in the real world, the natural order built into the process turns out to be the same as the temporal order in our actual space-time. So we can now say something more specific about how our world prevents logical contradictions. It seems to be the case that the way in which our world prevents logical contradictions, at least in the regimes that we have currently probed, which don't include things like closed time-rate curves, is by limiting us to implementing causal processes. So the requirement that all processes are causal, of course, also imposes requirements on how various processes can be composed together. So in particular, the mathematics of composing process matrices is actually quite complicated. In particular, composing two valid process matrices does not necessarily give another valid process matrix. So you have to put quite complex requirements on the way in which process matrices can be composed if you want the composition to produce something else which is also a process matrix. And similarly, if you compose two causal process matrices, the result will not necessarily be a causal process matrix. However, looking at the heuristic definition of a causal process matrix, it's quite straightforward to see what you have to do if you want your composition to remain causal. Roughly speaking, the composed process will be causal, provided that the two partial orders associated with the individual processes are joined together in such a way that you end up with a partial order for the whole process, which is acyclic. So you can imagine sort of drawing some kind of directed graph associated with the partial order for each of the two processes individually. So there'll be kind of a flow of arrows through the two processes, and then you're going to want to join it at the head of one arrow to the end of another arrow in such a way that all the two graphs combine together into a directed acyclic graph. And provided you do that, you have a guarantee that the resulting process will also be causal because you know that it's compatible with the existence of one composed strict partial order which has again, the process, which has the consequence that the outputs of laboratories later in the order only depend on the inputs of laboratories earlier in the order. If we note also that in our actual world, the partial order associated with causal processes is just temporal order, we can give kind of a heuristic statement about what is required for compositions of processes to be causal. Roughly speaking, we need to require that the output of a signaling process which is oriented forwards in time can only be used as the input to another signaling process which is also oriented forwards in time, because then clearly we will always get a process graph which is acyclic. So the word signaling appears in that definition because if you think back to the definition of a causal process, that definition was about which laboratories depend on the inputs to other laboratories. That dependence is in the sense of explicit statistical dependence, that is, it's in the sense of signaling. So the ordering requirements that appear in the definition of a causal process only apply to parts of the process that are signaling. It isn't necessary for things like the Bell correlations, for example, to be ordered in this way, because you can't create contradictions of the kinds that are discussed by composing non-signaling Bell correlations. So therefore, all these consistent chaining requirements apply specifically to signaling processes. So we can say now that we can be sure that our world will avoid having logical contradictions in all processes obeying consistent chaining. But what I want to emphasize about the consistent chaining requirement is that although the way it's defined here looks very temporally asymmetric, in some sense that's not really the case. You can see that because if you take a process which obeys consistent chaining as defined here, and then you rename all the inputs as outputs and vice versa, and you also switch the direction of time, the result will of course be another consistently chained set of processes with the direction going in the opposite way. So basically when you change the direction of time, all you're doing is just switching the directions of the arrows in your directed acyclic graph. So what that demonstrates is that this consistent chaining requirement, despite the appearance of temporal asymmetry, it really doesn't require any underlying objective asymmetry. It's in fact about the structure of the processes and the way they're joined together, but it doesn't require us to describe the processes as going in one direction or the other. Roughly speaking, we have two different directions, and the way we should think about the process is not to describe it as going one way or the other, but in some sense it's just being the equivalence class of those two possible directions. So finally, we can go back to agents and think how agency fits into this picture. So, in loose terms, we can think of agents as also being processes, right? An agent takes some inputs in the form of memories, sense data, and so on, and produces some outputs in the form of decisions and actions. So if our universe has this restriction that all processes must be composed in a way that obeys consistent chaining, that presumably applies to agents as well. Which means that if I am an agent deliberating in some temporal direction, that is, I take memories and inputs from one temporal direction and produce outputs in the other temporal direction, it follows that the output of my decisions in this deliberative process can only be used as the input to a signaling process if that process has the same temporal orientation as the deliberative process. So this is to say, if my decision is produced later than my inputs, according to some choice of direction of time, then I will only be able to use that decision as the input to a process if that process produces effects which are even further on along the direction of time. So that is essentially the temporal asymmetry of influence, right? If I am oriented in some direction, if my deliberative processes are oriented in some direction, then I will only be able to use my decisions as inputs to other processes which are also oriented in the same direction. So therefore, I will find that I'm only able to use my decisions to affect the future and the past. Furthermore, agents, of course, don't just make one decision. An agent makes many decisions in the course of their lifetime, and normally we expect that decisions I make later in my lifetime will depend in some ways on the decisions I have made earlier in my lifetime and the consequences of those decisions. So we can describe agents as being a sort of chain together. An agent is a set of decisions chained together in some sort of consistent way. And therefore, if agents obey consistent chaining, it follows that agents will need to have a consistent orientation throughout their lifetime. If my first decision takes an input closer to one direction of time and produces an output further away from that at that end of time, then all my other decisions will have to be oriented the same way, otherwise we will have violations of consistent chaining. So I will indeed find that all my decisions are oriented in the same way, and all my actions have causes pointing in the same direction of time, because if that were not the case, then we would have a violation of this consistent chaining requirement. So this way of thinking about temporal asymmetry of influence, I think, fits in very nicely with the perspectival view of causation advocated by Price and Ramsey. So they suggest that the asymmetry of causation should be understood as originating in de facto asymmetries in our own temporal orientation as physical structures in linear time. And that is exactly what the consistent chaining approach gives you, right? Because we've seen that consistent chaining structures don't need to be founded on any underlying objective asymmetry. You can have perfectly symmetric processes, and nonetheless, if you are an agent embedded in the process with your memories at one end of a deliberation process and your decision at the other end of that deliberation process, then you will find that you have to keep going in the same direction along that sort of consistently chained process. So it's a bit like walking along sort of a perfectly symmetrical hallway where you are required to keep going in the same direction you started. Objectively speaking, that hallway is perfectly symmetric, but nonetheless, once you start walking down it, there is a very strong asymmetry in a perspectival sense because you can only go in one direction along that hallway. So this way of thinking, I think, potentially helps address some things that were left a bit unaddressed in the approach suggested by Price and Ramsey. So in particular, one suggestion they make is that the origin of the temporal asymmetry of influences is to do with the temporal orientation of deliberation, the fact that we are always contemplating actions in the near future with respect to the time of deliberation. The problem with that claim is that it doesn't rule out the possibility that having produced my decision in the future of my deliberation, I could then use that decision as an input into some process which would have an effect in the past. And indeed, Ramsey and Price explicitly acknowledge that this is possible according to their notion of causation. And in fact, I think they see that as an advantage because, of course, Hugh Price would like to leave room for the possibility of sort of explicit retrocausality. But the problem then is that it seems like their account then doesn't explain why we don't frequently find ourselves able to produce effects in the past. Whereas if you combine that perspectival picture with a consistent chaining requirement, we can then see exactly what's going on. Once you produce your deliberation your decision in the future of your deliberation process, you're only going to be able to use that deliberation as an input into a process oriented the same way. And so that seems to explain why it is that we don't, at least commonly, find ourselves able to use retrocausality and to produce effects that are in the past relative to our deliberation process. Price and Ramsey also suggest that perspectival asymmetries must ultimately be grounded on some kind of objective asymmetry. Of course, they identify the objective asymmetry as the thermodynamic gradient. But the consistent chaining approach offers a different view on that picture because, as we've noted, that in the consistent chaining type structure, there doesn't need to be any objective asymmetry. You will still have this requirement that you have to keep going in the same direction, even if everything underneath is perfectly symmetric. Now, that of course does not mean that thermodynamics is irrelevant here. In particular, I think thermodynamics is probably very important in explaining why there is anything like a meaningful perspective in the first place. In order to have something like a perspective, there needs to be something like the formation of records and the use of records to produce actions. And so I think thermodynamics does play a very important role in explaining where a perspective can come from and how there can be such a thing in the first place. And I'm doubtful that there could be any meaningful perspective in a perfectly temporal symmetric universe. But once you have that perspective, I would argue that it is consistent chaining and not thermodynamics which keeps it moving in the same direction. Putting those things together explains why it is that even though our existence as perspectives might be grounded on thermodynamics, nonetheless the restriction that prevents us from changing the past is really a solid, 100% impossible thing to do rather than just it's unlikely and statistical. Furthermore, I would also suggest that the thermodynamic gradient itself, in order to define the meaningful thermodynamic gradient, in some sense you kind of need the consistent chaining underneath to start with. That's because you're not really going to get any kind of sensible gradient if all of your processes are just going around in loops and returning to the start, right? You need to keep going in the same direction in order for something to monotonically increase. So I think there's a really interesting interplay here between thermodynamics and this underlying consistent chaining approach that we're sort of seeing emerging from this process picture. And the two pictures can work in harmony to give, I think, a more complete description of what is going on in terms of the temporal asymmetry of input. So finally, I'll just finish by making some comments on indeterminism, because, if you recall, the argument I originally gave about logical contradictions arising from closed causal loops assumed that the processes were deterministic. That is to say, maybe there's some kind of probability involved in whether or not you succeed in implementing the process, but when you do implement the process, it's deterministic, and so this composition will deterministically produce a logical contradiction. But perhaps a more realistic way of thinking about processes would be to say that really all processes are at least a little bit indeterministic. And if the processes here aren't indeterministic, then you can't sort of derive an immediate logical contradiction in the same straightforward way. So for example, suppose two processes, rather than being perfect identity channels, subject to small errors such that each process has probability 99% of producing an output equal to its input. Then when we chain them together as shown here and we implement a bit flip operation for function g, we don't necessarily use a logical contradiction. We can avoid that by simply saying that one of the processes produces the wrong output. It produces an output that is the opposite value to its input, then there's no contradiction and everything works out fine. So it might seem that it's not clear that we can define consistent chaining requirements if we allow the existence of indeterministic processes. However, I would note that if you created a large ensemble of loops like this with our sort of slightly error compatible identity channels, then evidently what you're going to find is that every time, if there are no logical contradictions, every time you implement one of these loops, one of those processes must produce the wrong output. So rather than having probability 99% of producing the output equal to its input, it seems that when you implement the processes in this particular composition, we have only probability approximately 50% of producing an output equal to its input. And so recall earlier we sort of defined processes by appeal to their probabilities. We said a process is, the identity conditions for a process are determined by the statistical regularity it considers. So I think the correct thing to say about this kind of scenario is that if you find that whenever you implement process P2 in the context of this particular composition, it exhibits probabilities 50% rather than 99%, it seems like you have just failed to implement the process you intended to implement. You're just implementing some different process. So what that means is that as long as we sort of have some level of rigidity about the connection between processes and the relative frequencies they're supposed to produce, it follows that consistent chaining requirements will still apply to indeterministic processes as well, because if you are really succeeding in implementing process P2 and P1 in this situation, then they must both produce the same output, the output equal to the input in roughly 99% of cases, and then you will certainly get some logical contradictions. So providing we have some fairly rigid connection between processes, probabilities, and relative frequencies, we will still end up deriving some kind of consistent chaining requirement. So that's basically all I had to say. I just want to finish by noting that process matrix formalism it's still quite a new research program. There's a lot of activity still going on in it. So I think there are interesting questions that still to be addressed, and there's new possibilities that will presumably come out of this research program. But even with the sort of fairly early stage that it's in, it does seem to me that there are some really interesting connections between the ideas that are being developed here and some traditional, long-standing questions in the philosophy of time and causation and temporal asymmetry. So I'm really interested in seeing what kind of arises out of that. One question I particularly highlight that I'd like to see an answer to is about why we don't see all the valid causal process matrices in nature. So if you recall, we see only the causal process matrices in nature, and we don't as far as we can tell, appear to see the other kinds of process matrices which are not causal, but that those processes can't be ruled out by the no contradiction requirement because by the definition of a process matrix, they won't give rise to contradiction. So there's still a sort of open question about what it is that sort of forbids those processes specifically and allows only the causal ones. So I hope that the future work, either in this research program or in philosophy, might perhaps clarify the question of why we get this specific set of processes. So yeah, thank you very much for listening, and I guess we should see if there are any
I wanted to just start off to make things clear. I don't know whether there's some language differences or philosophical differences that let me not appreciate what you're doing.
Yeah.
And part of it is also my hearing.
Sure.
At the beginning, you talked about changing the past.
Yes.
I know what it is to change my socks.
Yeah.
I don't have the vaguest idea what it could be to change the past or the future.
Yeah.
So, and then you start talking about influence. That I can understand.
Yeah.
And you went, and I sort of missed, you just went from one to the other.
Yeah, so I intended the term change fairly loosely to express the intuition that we have that there's something different about the future and the past. But I agree that in some sense one is not really changing either the future or the past, and it is best to talk about this in terms of influence. The word change was just a way of describing this sort of common sense intuition we had about the past and future having different status.
The other thing was connected to this, you seem to think the statistical account had the consequence that every once in a while you really would change the past. But that's not what the statistical account says at all. It just gives an account of influence in terms of probability.
So again, when I said change there, I was using that in loose terms, but what I meant was that the statistical account seems to give the impression that if we can influence, if we understand influence in these terms, it seems like we should have at least some possibility of influencing the past, which is somewhat in tension with the intuition we all have that the past is totally outside of our control. So the question was, how can we reconcile the sort of statistical and approximate nature of the temporal asymmetry in the statistical account with our intuition that really the past is totally outside of our
I do think it's outside of our control, when you understand what control is. But the statistical account says you can influence the past, but in a way we don't care about, we don't notice, it's negligible, it's just microscopic.
Indeed, and I think for some people that seems very odd because, for me, for example, I don't know what I could do to influence the past, even if it is negligible and microscopic. It doesn't seem to me that I have any actions available to me or any processes I could use which would have any kind of influence whatsoever on the past. And I think if you look at the sort of process description of nature, that gives a different kind of approach where, in fact, it is really just totally impossible for me to influence the past, even at a microscopic level. So I think these approaches could
One
work.
thing I'm worried about,
Yeah. The approaches I think could work together. I don't think they're contradictory, but I'd like to think more about how they could be fit together.
Okay, thanks. So David,
I guess this is in the nature of pressing Barry's question a little further. It does seem that the worry about contradiction is going to arise only if change means change, not influence in the sense that we're talking about in statistical mechanics. I mean, the way we talk in these statistical mechanical approaches about changing the future and not the past is it just comes down to a question of whether there are counterfactual dependencies going in both temporal directions or not. But what you get when you evaluate those counterfactuals is a counterfactual entire history of the world, if my finger had been here instead of there. And of course it's a feature of this that the counterfactual history of the world, whatever it is, and however you evaluate counterfactuals, as long as they're more or less temporally symmetric, and as long as you're not talking about miracles, these are going to be solutions to the equations of motion. Insofar as the equations of motion are not self-contradictory, okay? Insofar as these are solutions, they're of course not going to contain any contradictions. So, I mean, I think the passage from, that is, I think Barry's question was really relevant here. There's a big, big difference here between influence and change, okay? And where all you understand yourself as meaning by influence is a counterfactual dependence. It seems like in the absence of closed, general relativistic closed causal loops or something like that, as long as you've got solutions to the equations of motion corresponding to all these possible boundary conditions, there just isn't any, the claim that you can influence the past raises absolutely zero threat of any kind of a contradiction.
So I 100% agree that the standard counterfactual meticulous account does not lead to the suggestion that one could create this kind of contradiction. What I wanted to motivate was the thought that, however, whether you describe it as change or influence, and I do actually think that's to some extent a semantic distinction which doesn't matter all that much here, whichever way you describe it, there have to be limitations on the extent to which you can influence both the future and the past. You cannot consistently believe that you have the ability to create the kind of contradiction the composition I showed here.
Yeah.
So there do have to be some kind of limitations on what kind
Yeah,
of
but
influence
I don't understand why it doesn't suffice to impose those limitations just to say whatever it is that would have happened if my finger was here as opposed to here is another solution to the equations of motion. As long as we have that, okay, we know we have no threat of contradiction.
Yeah, so again, my concern is not that the meticulous account does lead to the possibility of contradiction. My point is rather that if you think seriously about the fact that the structure must be defined in such a way as to avoid contradictions, that produces another way of thinking about the reason we can't change the past. And that other way of thinking about it is that necessarily the kinds of processes and actions available to us must have the property that they don't lead to these kinds of contradictions. And it seems that leads to some kind of consistent changing type of requirement where actions are changed together in ways that point in consistent directions. So again, my point is not to say that this is in any way contradictory or in tension with the meticulous type account, but rather that this seems like a different way of arriving at that way of thinking that we must have this feature in our modal structure.
Yeah, it's not exactly on that, but it's sort of in the similar ballpark. At least at the start of your talk, sometimes it seemed like you were cashing out influence in terms of what agents can do.
Yes.
And I'm wondering how exactly you understand this word can, and whether it is what you actually want for your purpose. So one view one might have about the word can is that it's highly context sensitive. Compared to a dog, I can speak Finnish because I have the right, musculature and so on, speech organs. But relative to compared to a Finnish speaker, I can't speak Finnish. And similarly, you might think a time traveler, they can kill their grandfather relative to, them being like an able-bodied male or female or something and having the weapon and being a good shot and so on. They can't kill the grandfather relative to, given the context that they are actually a time traveler and, it wouldn't be born, or the fact that the person in front of them is actually their grandfather and so on. And given this context sensitivity, I'm wondering whether there are actually any deep differences about what you can and can't do in the time travel case versus the ordinary case. Even in the acyclic case, I can do something relative to, maybe the past and so on. I can't do it. I can't jump out of the window relative to the fact that I'm actually not going to do it. Anyway, so I wonder whether you can comment a little bit on how you understand can, whether you agree that it's this context-sensitive thing and how the difference in the acyclic versus time travel case.
So I 100% agree that the term can is very context-sensitive, and I think that's precisely why both the meticulous account and this other kind of account also both provide, in some sense, satisfactory explanations of what we can and can't do in the difference between past and future. I think those approaches conceptualize the term can in slightly different ways, and both lead to sort of reasonable accounts of what we can and can't do, but they do that in different ways and by a field of different kinds of structures. So in this particular talk, as I said, I was thinking about can and can't as a fact about modal structure, which, for convenience and compatibility with the process matrix formalism, I was understanding in terms of some set of processes. I do think that is obviously an idealization. The world probably isn't really made out of processes in quite the simple sense that the process matrix formalism suggests. But I think that's a helpful way of conceptualizing modal structure in this context, because then we can then see what kinds of constraints the consistency requirements put on what the modal structure has to be in order to avoid the problems I've discussed here.
I mean, just a comment. I mean, the context-sensitive account would also be cashed out in terms of, can also be cashed out in terms of modal structure. Just it's just context-sensitive what facts you require to be valid.
That is what I just said was that the word can is context-sensitive, and one way of cashing it out would be the Wentaculus approach. Another would be this kind of modal structure. So there's with modal structure conceptualized in this particular way in terms of structure. I don't claim that either of those approaches is better, but I think they give different kind of windows onto the structures that we are dealing with in our actual world. In particular, I think this consistent chaining type feature is a structure that's really there in our world, and is helpful to understand from features of the way in which our macroscopic world is organized. So it is a useful way to think about things, even if not the only way to think about things.
So let's see, Yi and Stuart.
Yeah, it's kind of in the vicinity of the discussions, but I was also, and maybe here's a way I'm understanding based on your answers.
Yeah.
In the beginning, when you motivated this consistent chaining requirement,
yeah,
you made the observation that, you would be kind of like, it would lead to contradictions, you would allow the possibility that in some way you can affect the past so that it's different from what it actually is. It's like a contradiction. But then I was a bit puzzled because I think that observation by itself is temporally asymmetric, but also true about the future, right? Like the future cannot be different than what it actually is. So later I was then maybe thinking that what you're trying to do is maybe thinking that you're assuming like an asymmetry, a temporal asymmetry, and then you're trying to say that the asymmetry, once you assume that maybe the thermodynamic asymmetry, and then you impose this consistent chaining requirement, that's how you get the asymmetry influence or something like that. Is that maybe a correct way to interpret what you're doing? Or?
No, because the consistent chaining requirement in and of itself doesn't require any asymmetry. So the point is that, again, that not that one can literally change the past or the future in the sense that one goes into the block universe and adjusts some value. The point is rather that when we describe in sort of modal terms the structure of what we can and can't do, and what we can influence and can't influence, there's necessarily a trade-off between what we can influence in the future versus what we can influence in the past, because our influences must be limited in such a way that we can't produce contradictory scenarios. So however you choose to make that description, there does have to be some kind of constraint such that if I take myself to have complete control over the future, I must have basically no control over the past, or one could imagine sort of more intermediate possibilities. But that statement is temporally symmetric in that if I instead describe myself as having influence over the past, if that's the way we conceptualize it, then I would have to have no influence over the future. So it is a temporally symmetric requirement, and it just involves a trade-off between having influence over the past and over the future.
Stuart.
I very much appreciate your description of the asymmetry. In particular, I've been struck by something you said, which I actually completely believe that's true also, which is that there's a fundamental difference between time direction and time order.
Yeah.
Time order has a logical structure.
Yes.
It is not time dependent. In time order, you don't have spatial time dimension where there's a forward towards the future and a past direction. There is no direction. And that would seem to resolve most of the issues concerning time travel, causal influence, so on and so forth. In particular, we tend to look at a Newtonian universe of cause, effect, and things like that. With entanglement, especially in entanglement that's outside of the light cone, we talk about distance very often, but we can also talk about time outside the light cone. And so there are experiments that have been done where you do the exchange of an entanglement with some particles. And you can stretch this that a particle existed, you might linguistically call it the past, and another particle that's in the future. So this one of the particles in the past no longer exists from that point of view. And when you would collapse the entanglement, the wave function, whatever, all of a sudden that particle, which you call in the past, now becomes a fact of the universe. Before then, it wasn't. In that sense, if you talk about past and future, you've changed the past. But I think there's no sense, either by convention, linguistically it's fine, but from physics, one should actually not talk about past and future, but should talk about the logical structure of time and the order of time. In which case, I think you resolve a lot of linguistic issues and logical issues.
Yeah, 100%. I think that it's really important to distinguish between sort of causal order and causal direction. And often when we talk about, we try to understand like macroscopic causation, we talk a lot about where does the direction come from. But in addition to a direction, you also need to have some kind of underlying ordered structure, right? You need to have that kind of structure such that when you add a direction to it, you end up with a directed acyclic graph rather than a cyclic graph. So I think the sort of the importance of this underlying consistently changed order is kind of missing from any of these discussions of causation. And I think in particular when physicists talk about causality, in fundamental physics in particular, what they're talking about usually is actually something like causal order. It's to do with how things are chained together consistently, and it has nothing to do with any particular direction. So I'd like to see more of a distinction made in these discussions between causation in the sort of directed sense and causality or causal order in this undirected, consistently changed sense.
Yeah, so it struck me as kind of foundational and somewhat assumed here, this great fear of logical contradictions within the universe. And I was wondering if you could say just a little bit more to motivate that, since of course there are those out there who will say that there actually are logical contradictions, semantic contradictions, perhaps even physical contradictions that we find in our universe. So I was wondering if you could give just a little bit more than, speak to it a little bit more than just the assumption that this is something to be avoided and feared at all costs.
Yeah, I mean, and I take a sort of fairly realist, physicalist view of the contents of reality. And it seems to me a very reasonable thing to say in that picture that I expect the physical facts about the universe, whatever they are, to not contain any contradictions. If one takes a less physicalist and more sort of idealist approach, there's certainly room for the possibility of logical contradictions. And in particular, there are some interpretations of quantum mechanics which suggest that the physical descriptions are always relativized to some observer. And in that kind of picture, you certainly can have cases where relative to one observer, a value has a variable has some value, and relative to somebody else, it has a different value. So kind of the starting point of this project is the assumption that we are working in it. We're not working in that kind of picture. We are working in a picture where there exists some kind of independent third-person description of what there is in reality, and by definition, that description can't contain contradictions.
I mean, I'm just going to push you a little bit on that, because I'm not sure that I agree with the idea that you can't be a realist
realist and also accept there are logical contradictions within the universe. I personally identify as realist, and you could just take things, a simple example that's a common one that people go to is the liar paradox as an example of a semantic contradiction. I don't think that requires any sort of anti-realist.
Sorry, when I said contradiction here, I'm referring specifically to the case where some physical variable has the same value, has two different values in the same space time point. So that I would characterize as a physical contradiction rather than a semantic contradiction. I, like you, am not all that concerned about semantic contradictions, but it seems natural within the kind of picture of reality that I tend to be attracted to say that you can't have that kind of physical contradiction. I don't claim that's the only possible kind of description of reality, but I do think that making that assumption that there are no physical contradictions is a useful and really productive assumption, because you can explain a lot of things about the way our world is, in particular, what kinds of processes are available to us, based on the assumption that they must avoid making contradictions. And so, for example, one can explain why we have non-locality in quantum mechanics must be no signaling on that basis. So I think that although there could be other possible pictures of reality, this is a good picture of reality in sort of the theoretical sense, in that it leads to explaining lots of things and is very productive.
So then, is there a reason why the requirement here was to always avoid logical contradictions versus, which I took to mean contradictions in logical space versus contradictions in gnomic space, physical space, however you want, or metaphysical space even, however it is that you want to characterize that. It seems that the requirement of avoiding contradictions here was perhaps a lot broader than what you were really after.
Sure, perhaps I should have phrased that in terms of physical contradictions. I think of a physical contradiction as a class of logical contradiction, but I agree that there are other kinds of logical contradictions which are perhaps not ruled out by the kind of approach I'm taking here.
Thanks. Yeah, you want a question, but can I just ask you a question? Are you also not a realist?
Oh, no. I identify as a realist. But I might have some other thoughts that are rather perverse.
I suppose the logic of mine is something outstanding.
I mean, look,
follows from a contradiction.
I will tell you that I have non-classical sympathies, let's put it that way. I've hung around Graham too much.
Okay, yeah, so just a small scientific question. There was a slide where you were going around three alternatives. The one is just processes. The model structure does not allow processes which could give rise to contradiction, and you're using could there. So it's just another question about could. And then two, the model structure could in principle give rise to contradictions, but arranges accidents or interferes with free choice. So the question is, are you using could in the second, in point 2, in the same way in which you're using could in point 1?
Yes.
Yes.
So in both cases, the word could here is being used to refer what is mathematically possible given the set of allowed processes.
Okay, so
sorry, I didn't have much space on the slide to write this.
No, yeah,
That's
sure.
what's
So maybe this is something about the process matrix formalism that I don't understand, but so suppose that 2 is true. And that model structure could in principle give rise to contradiction, but arranges accidents or interferes with free choice to prevent contradiction. That means that is it necessary that the model structure always arranges accidents or interferes with free choice to not give rise to contradiction? Because if that's necessary, then I would just say, well, the model structure could not give rise to contradictions, right?
Yeah, so again, the word could here is being used to refer to the modal structure does contain processes which is mathematically possible to produce contradictions, like it might contain these processes here, but modal structure also has the property that the universe steps in and intervenes such that I will never succeed in implementing the bit flip operation here, or I will never succeed in implementing a particular composition. So the word could is being used in in the first part of that sentence, in a restricted sense, is applying to what follows from the mathematical definition of the processes, but then there's a different, broader notion of modal structure, which is assuming that, in some sense, the universe just doesn't allow us to do this.
Okay, so maybe, I guess that, so you're distinguishing like accidents and processes, maybe there's a sense in which a process could give rise to a contradiction in this mathematical way, but just some metaphysical essence.
Yeah, so in the sense that in that kind of picture, both of these processes, P1 and P2, are possible, and perhaps not only are they possible, but we have actually implemented them. They are definitely things that occur in reality. But then when we try to do this, when we try to create this composition, we just never manage to do it. We always break our leg first or something. So that there are two levels of modality here. One is the sort of purely just mathematically speaking, the processes seem that like they could create a composition if I could compose them freely like this, but in fact the modal structure of our reality doesn't allow us to compose processes freely in this way.
So that's the second alternative.
That's the alternative.
Okay.
Yeah.
So
the first alternative is just say that if processes P1 and P2 can't both be allowed.
Eddie,
Yeah, thank you, Emily, very interesting. So I have many questions we can talk about later, but I was thinking it's just conceptual question to for you to maybe say more is I kind of speculative thought because you and I have similar views on laws. On the Humean side, you can take this and think of it as a synchronization of what happens in regularities. But on the non-Humean side, I think the consistency condition feels more like constraining law than say a productive law that implies. It's more like, here's my global space, like possibilities are like this. But it's harder to give interpretation which have time and then production and so on. But given this constraint law picture, I think, is it possible, I have no idea, to get to the same thing from a different window as related to this? Namely, so you know that paper I wrote with Jeff Barrett on concerning probabilistic laws. Suppose you take the Wentaculus or statistical kind of theories with deterministic trajectories, but with some boundary condition probabilities. And don't interpret the probability as distribution of numbers on a bunch of worlds or histories, but a real constraint and rooting out some worlds and rooting in some worlds. And most worlds are rooting are going to be good worlds, and worlds that without magic worlds. I was wondering if, I don't have no, concrete framework to offer, but suppose you have some constraint in terms of frequencies of some regularities, plus the randomness of the initial conditions. Then is it going to automatically rule out those worlds in which you can do this thing? It's like, is this kind of typical or kind of effect atypical?
Yeah, so I have two things to say about that. One is that one of the motivations for this way of thinking is that if you start from a standard dynamical picture, there's a sense in which maybe you don't have to be too worried about this kind of thing because if your processes are just always going forward in time by definition, right? So it seems like once you move to a constraint-based picture, one thing you do have to be worried about is, well, what are the restrictions I have to put on my laws to ensure that I don't get stuff like this happening? And the way I define laws is, it's sort of roughly extensional way where laws correspond to sets of possible universes. And so in that picture, since each possible universe will not contain any contradictions, the laws are not going to produce any contradictions either. But we can then ask, what does that consistency requirement mean at what level of what the laws will actually look like to us from within our setting within the universe? And I think the answer is that there's going to be some kind of restriction on the way in which things can be chained together from our point of view, which will necessarily mean that the modal structure doesn't allow us to produce these kinds of things. But that is sort of an in-universe level description from the point of view of agents in the universe trying to compose things rather than the external description from the point of view of, from which point of view everything is sort of by definition consistent.
But in that case, will it be a meta law that constrains the actual laws? Or is it going to be a law for the set of possibilities? Will all possibilities be consistent?
Yeah, but I tend to think that you should be able to just define your laws in such a way that, if you think of laws as just picking whole histories at once, then because every history is going to be self-consistent, right? The laws just kind of by definition are going to be self-consistent. But then there's a further question about how you sort of write down what that actually means, what the laws might look like. And so that's kind of the idea of this project, to understand if you're not assuming a dynamical direction, what kinds of constraints are you going to see on your laws from this requirement that they've got to produce one consistent history.
Right. And do you think that this can actually work in such a way that we are ruling out those worlds that are atypical, or is it going to be unknown whether it's typical or atypical?
Yeah. So it's easiest to think of this as a deterministic case because then you don't have to worry about that. And the probabilistic case is more complicated, but I mean, as you probably picked up on, part of the argument of the probabilistic case was that it requires some amount of rigidity about what the relative frequencies are. And I think particularly that would link very nicely with your view where there is some kind of requirement that the frequencies fall in some regime. So I can see that those two views would potentially link quite nicely.
Yeah, but the third one.
Yeah.
Thanks.
Thanks.
It'll be okay if we break until 1:15, and then we'll have until 20 of to walk on to the rest of our okay.
Yeah, that's what I mean. All you need is a consistency. This is a distinction that I think it's because if I talk about something, it means it's different than what talk about what I'm going to have for dinner, changing what I'm going to have for dinner by what I do. So at some earlier time, I'm going to have a sandwich for dinner. At some later time, I'm going to have soup for dinner. It doesn't make any sense. It's exactly there's only one thing that I'm going to have. There's only one thing that I'm going to eat. You know, there's only one thing that can be right. How what I do and that's right. Of course. But to talk, right. Okay. So and the situation in which you worry that if you do something that changes what we will, that's exactly what you know. Yeah, because you have a range of things. So that there's no single right, but that's a if there were contradictions, there wouldn't be, the universe doesn't the world is everything that's the case.
Yeah, that's pretty interesting.
Yeah, I think it is, right. Yeah, it is. So this is like in general. I'll be.
Let me see if I can find, yeah, okay. I'll just go over, I guess there are other colors. Sorry, that was. They're all colors. Let's see
I guess I can see it with my glasses. Yeah. I think so. Yeah. Just read it when you say it. It's readable if you read it to us. I think if you say it first, people will know.
Yeah, it's more for me than for Yeah, I know, there's all kinds of stuff back there, but there's very little white. These are just reminders for me.
Don't worry.
Okay?
Yeah.
I'll show you stuff from my own case.
Right. Oh, right.
We'll talk later. Okay, let's begin our proceedings. Our next speaker is To Maudlin.
He needs some introduction, he's not, I think, he doesn't need to be staff.
You didn't give the other ones introductions either.
So, look, I don't have a presentation here. Barry said, oh, will you give a talk at this thing? And I said, sure, what do you want me to talk about? He said, I don't know, talking about non-locality, David's stuff. So I said, okay, yeah, we can talk about that. And I'm real, I'm like maybe many of you, I'm really tired, so you don't have to worry that I'm going to be all that energetic. But here are some things I think that are worthy to talk about. I guess the main topic I wanted to get into is a kind of debate that's been going on about so-called wave function realism. And I want to say some things that I hope are completely uncontroversial, but I hope will shed some light at least on how I think about this debate. Now, the first point to make is just this, unfortunately, linguistic one. There is a position one would, I think, reasonably call wave function realism sub-naive. That is, if anybody with any philosophical background, you just walked up to them in the street and said, I'm a wave function realist, they have an idea of what position you held. Then there is this wave function realism. Now, what I originally had was going to be trademarked, right? So I was going to do wave function realism trademark, and I said, TM, oh my God, I can't do that. That's exactly what I don't believe. There's the term wave function realism, which yeah, it goes back to David's paper, Elementary Quantum Metaphysics, and there is a position that's out in the world under that name, and although I certainly subscribe to this, I certainly do not subscribe to that, so we first have to get clear about what's what here. This thing, well, let me now, before I get to exactly what this says and what this says, let me again this is my standard picture of mathematical physics. Again, I take it to be pretty uncontroversial. Mathematical physics employs some kind of mathematical objects as purported or possible representations of physical possibilities, right, of how the physical world might be. So there's a representation relation between these things and these things. That raises lots of very straightforward questions about how that relation is supposed to go. One thing that can happen a lot, does happen a lot, is you get something like this. That is, you have a bunch of mathematically different objects, which, as they are deployed and understood, are supposed to represent one and the same physical situation. When that happens, we say that there's a gauge degree of freedom here, right? There's a gauge orbit or something like that, a whole bunch of these guys. And you're not supposed to think that choosing one or another in this gauge orbit indicates that you think something different is going on over on this side. Now, there can be disputes about what the gauge degrees of freedom in the mathematical representation are. We're going to see that the original, at least naive version, I don't know if David's changed his mind about this. One way to see what's at issue here, one thing that's at issue between these two positions, is that by David's initial position, his view about what counts as a gauge degree of freedom here is not the standard one. That is the standard one a physicist would accept, right? Whereas there's nothing in this that forces you immediately to change that, right? So that again, so what do I have in mind here? Well, now there's then there's also the question of understanding these things just in terms of their ontology, right? What, right? So over here, the ontology, these are mathematical objects. You want to do their ontology, fine, you're doing philosophy of math. Interesting subject, not our subject. On this side, you think of these things as physical possibilities, and then here to articulate these, you want to give an account of what the fundamental physical ontology is. It could have a space-time structure. Then there can be a debate about what is the ontology of space and time. You can get into substantivalism versus relationism there. There can be different forms of matter. There can be fields. There can be, well, we're going to get to this, right? Well, I'll just put it here. Good. Now, one thing there's no real debate about are the mathematical objects that are used, at least in standard non-relativistic quantum mechanics, is usually where we begin. One of those mathematical objects goes by the name psi. And if I ask, well, mathematically, what is it? Mathematically, it is, this typical thing used here is a complex function, or maybe a spinorial function on a large dimensional space. On a large D space, and that large D space is commonly called, quote, configuration space. Good, that's all the math of. One of the standard things that's done here in terms of the gauge, by the way, just to say this, and so you say, oh, wave functions are are raised in a Hilbert space where the elements of the Hilbert space are complex valued functions, these complex valued functions, space of functions. Are elements of the Hilbert space. Now you say, oh no, wait, I don't quite want that, because if I take one of these gadgets and I systematically change it mathematically by a global phase transformation, that's supposed to represent the very same thing. That's mathematically different, right? These are two different these guys. But you say, no, that's just a gauge transformation. The overall phase of this thing doesn't correspond to a physical degree of freedom over on this side. Yeah? If you do that, by the way, the natural thing now to say is, so what really represents in a more one-to-one, what you kind of would like is a one-to-one map, right? What would be really nice is to have a one-to-one map from the math to the physical possibilities, where you don't have a one-to-one map. You have to worry about these gauge orbits and so on. So, you know, one thing you do is you just formally kind of divide out the gauge degrees of freedom, and you say, no, really what I want to be doing with here are elements of projective Hilbert space. Not elements of Hilbert space, but elements of projective Hilbert space is the technical thing we use. On the normal picture, you think, gee, the physics, I mean, you might think the physics ought to go much more easily if I just deal with elements in projective Hilbert space, because in some sense, they're the things that one-to-one correspond to what I think are the physical possibilities over here. It's a curious thing that you just can't do the math very easily on rays in projective Hilbert space. I mean, these phase things are important, and, you know, so there's something to think about. It's funny kind of mismatch. Anyway, so back here. So you're using this psi thing. Certainly you're using it in the math. Then the question comes up, well, what, if anything, does it represent over here on the physical part, right? Especially the physical ontology part. In particular, what does it represent about an individual physical system? Ultimately, take the universe as an individual physical system, but you could have little subsystems, you assign them little wave functions. And there are various possibilities, as we know. One possibility is to say, it doesn't represent anything about an individual physical system, per se, right? Well, what does it represent? Well, the statistical view, this is what Einstein sort of wanted to push, it represents only statistical characteristics of collections of individual systems, right? Okay, that's a thing in the world, statistical characteristics of collectives. That would have the consequence that if I pick up pick up one system, at least intellectually, and regard it no longer as being a member of this collective, but now regard the very same system as a member of that collective, the psi function could change, because it's not attempting to describe that individual system. And if it's describing something statistical, it's going to depend on which collective it's part of. That would be fine. Would you then say that this represents something real? Well, not about the individual system per se. Right? You could say it represents something real about the collective, but you would say it's not real about the individual system. And there's another view that says, look, this thing, this gadget we use, that doesn't represent anything about any physical system. That represents something about our beliefs, our knowledge, our information. This is the kind of thing that Chris Fuchs goes around and says that psi should not be stuck onto the system, it should be stuck onto your forehead. He says that. I didn't make that up. He says that. That's the view. They don't exist, as it were, in the world. Now, I take it, when David wrote his, and David's paper was just the beginning of all this stuff. It was long, and you know, he's had time to reflect, and maybe he doesn't. But this was part of the thing, saying, look, you just can't understand actual phenomena in the world on either the statistical or the subjective viewpoints about psi. Because too much stuff just depends, you know, do two-slit interference with the particles one at a time. So you see interference bands. In some sense, the interference is there on every run. That is, the fact that the wave function is interfering is preventing spots forming on particular parts of the screen every time. So even for a single particle, right, this interference is something physical going on. And so this psi ought to be representing some actual objective physical feature of individual systems. That's what I take this to be, right? This is just the rejection of the statistical understanding of psi and the epistemic or subjective understanding of psi. And, you know, in the places I grow up, all right-thinking people believe that, okay? So, you know, if you're gonna raise questions about that, now we're in an entirely different problem. But what David then asked, okay, so it represents this thing over here under some interpretation, maybe we still have to sort out what the gauge degrees of freedom are, really represents some real physical characteristic of an individual system, physical system. But what does it represent? Okay, what is this thing it represents? And in the paper, David says, well, clearly, where the clearly comes from looking at this mathematical structure, it's a kind of field, right? Or two fields, in fact, because it was complex value. The original suggestion is that there are two fields there. One that, as it were, well, I'm not sure, it could go either way, but I guess one that corresponds to what we would normally call the real part of this and the other to the imaginary part. I guess you could do one to the magnitude and the other to the phase, you know, anyway, there are two mathematical degrees of freedom, because there are two mathematical degrees of freedom in specifying a complex number, even more if you go to the Spinorian structure. And David just wanted to take those mathematical degrees of freedom and, as he might say in a very flat-footed way, say, what could the world be like such that there's an object in it that's perspicuously represented by this kind of mathematical object? He said, a pair of fields. But of course, there was this issue that it's a pair of fields mathematically on a very large dimensional space, right? In fact, a space of kind of familiar dimensionality, if you're talking about what we naively call an n-particle system, the space has 3 n dimensions, and it corresponds mathematically to what we normally call configuration space. Now, if you think of a field, right, what is this thing, right? So a field, I mean, we said there are all kinds of ontological questions you can be asking here. When we talk about what is the fundamental structure, nature of the space-time structure, that actually direction of time, substantive relationism, all kinds of stuff comes in there. I have opinions about all that stuff. What kind of matter is there in this structure? Are there particles? Are there things like electromagnetic fields and so on? Are there matter densities, or these are things that might exist? But one thing is a field, and we get this idea of a field from thinking what we learned about classical electromagnetic fields, learning Maxwell's theory. So David, I think it's fair to say, had that picture. It was like, what else could it be? The wave function. What could it represent? Now, the thing the wave function represents, I call the quantum state, just because I want to make a linguistic distinction between you can ask about the mathematics of this thing. This lives in the mathematical object side of this. And you want to say, okay, if I'm a wave function realist, this guy represents something over on the ontology side, call it the quantum state. Now, I guess David's view would be the quantum state just is a field. But what happened was then he had to say, well, of course, if a field is like an electric field, magnetic field is some thing that has possible physical. Yeah,
just a question of clarification.
Yeah.
I mean, something that you call some kind of a state doesn't sound like it's a thing, like a field sounds like it's a thing. You were saying
I'm not,
the quantum state would just be the field.
As you know, at the end of the day, my view is that this gadget exists and does not correspond to any of the familiar kinds of fundamental.
Right, but you were saying something about what my view must be.
Your view is that it's a field.
That the quantum state is a field? Or
No, I define the quantum state as the thing represented by this.
But you've got an arrow going from quantum state to.
Yes, so I said, so now you can disagree.
Okay.
By definition, I call the quantum state whatever this thing represents.
Oh, I see. Okay.
You think what this thing represents has the ontological structure of the field.
Sorry.
Right, so that arrow was you.
Okay.
Is that fair?
I think so, yeah.
All right, but of course the price you have to pay for that, if you want to analogize the thing to the electromagnetic field, is you then have to take this space on which this field lives ontologically seriously. And as I understand wave function realism sub Albert, by ontologically seriously, it means you just take it as primitive, or at least very deep in the structure, that there is a very, 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 very large fundamental physical space, much larger dimensionality than the one we think I'm waving my hand around, which is only three-dimensional at macroscopic scale. And I think the rhetoric in that paper was, okay, physics sometimes tells us surprising things. And anybody who wants to be serious about taking quantum mechanics seriously as a proposal about the physical world, surprisingly, you're going to have to fundamentally rethink your beliefs about the structure of fundamental spatial structure of the physical universe. Right?
Sure.
Okay. We can get it. So this is fun. I'm just trying to present it as I understand it, so you can correct it, right?
Yeah.
Then there was a whole little byplay of people saying, well, there's the two-space theory. Then you say, but what does something going on in this high-dimensional space have anything to do with the present in China, right? I mean, what does that have to do with my waving my hands around? In the kind of version of Bohmian mechanics that's produced by David in this context, which is not the version that anybody else ever was thinking of. Yes, there's this large dimensional space. There is on it a field or a pair of fields or a quadruple of fields or whatever. And in addition, there is a single point particle, which Shelley helpfully called the marvelous point. And that, the fact that I am now waving my hand around apparently in three-dimensional space, that fact is somehow to be understood as a rather cryptically coded claim about how the single point is wiggling around in this immensely high dimensional space. Right? All the structure, all the familiar spatial objects in spatial structure, the shapes of things, the motions of things, how many things, how big they are, all of that, which we, in a kind of naive way, if we had particles, would say that's the collective result of the dispositions of a whole bunch of particles making up this table and a whole bunch of different particles making up this, and these are shaped this way, and that's doing that. All of this somehow gets reduced to the motions of the marbles. Now, of course, everybody understood from the beginning that there is the reason why this thing seems maybe not so hard is because you call it configuration space, and you say, look, even in classical physics, we talk about configuration space, and it has 3 n dimensions, and phase space, and it has 6 n dimensions, and blah, blah, blah. But of course, in that setting, we already know what the ontology is. It's n particles in 3 space. And the configuration space is simply a convenient mathematical object that's introduced to represent over here, say, n particles in 3 space, right? That's in the ontology. And what David somehow wanted to argue is, no, the ontology really is 1 particle in 3n space, which you can then see the representation relation here becomes much easier in a way. But then understanding, and as Shelley would often say to me, when I couldn't quite understand what he was, when I was making objections originally to Bohmian mechanics, and I'd say, I don't need, he'd say, look, this is a theory of something. And from that point of view, I understand David's theory. David's, the marvelous point theory is a theory of something. It's a theory of a single particle moving around in an extremely high dimensional space. It's just, I can't, then you say, but what does that have to do with spots on screens and, coins and cats and dogs and stuff like that? Right? And then there's that produces a problem. Now, my take on this, well, now there are 2 questions, right? What are the other options? And why the hell would you want to do that anyway? Right? What was the motivation? Now, I've just given a motivation which is very naive. It just says, well, I've got this psi function sitting over here. We all agree, has this mathematical form. If it were naively a pretty direct representation of something, it looks like it might be a representation of a field or several fields on a high-dimensional space. Let's go with that. There's something else that shows up here, and that comes back to Bell's theory, which up until now, you might think, this has nothing to do with Bell's theory. What am I talking? It's just about what is the ontology of quantum mechanics. What does it have to do with Bell's theorem? Well, we all know Bell's theorem, I hope we all know Bell's theorem actually rests on 2 fundamental postulates, neither of which is reality exists, right? That's not. One has a perfectly good mathematical form called local causality, and that basically says, well, if we put it in a relativistic context, that all of the causes of an event like this have to lie in or on its past lifetime. Or if conditionalizing on this, I get a probability for this, if I further conditionalize on anything at space-like separation or in its future, well, its future, of course, can be changed. But if I further conditionalize on anything at space-like separation, I will not change that probability. Right? Which of course is relevant when you're looking at entangled photons and whatever, where the prediction is, say, the chance of spin a half being up here is a half, and then there's this other particle, the other entangled pair that's being measured over here, and its probability is a half. But if I get to, if I now get to condition not just on how these things were formed back here in their common light cone, but I can condition on what happens in the other guy, then this goes up to 1. Right? So that violates the condition of quote local causality. Not about signaling. Not saying I can control any of this. It's just, right? So Bell says, let's assume that things are local, and let's assume this condition called statistical independence, which basically means Alice and Bob can set their devices however they want, and there will be no long-term correlations between how they set their devices and anything interesting about how this pair of particles was created. And people are so desperate. There are people so desperate to maintain this as to deny that. I won't go into that particular pathology. Now, part of David, I think, part of David's motivation, and certainly part of the motivation, and Alyssa May has recently, written a book about this position. And when you read that book and you look very, with an eye to, well, okay, I understand what you're doing it, but then you ask, why are you doing it? Over and over, the answer comes back, I want a theory that's local and separable. I want a theory that's local and separable. I want a theory essentially that you'd sort of think you can't violate those. And there's the fundamental curiosity is just to think through. I mean, you can sort of understand why you would want that out of a kind of sense of, I don't know, nostalgia or something. That's what I learned, right? All of classical physics. What was characteristic of classical physics? In classical physics, arguably, all of the ontology is local. Like particles, it's always somewhere, right? You can tell whether there's a particle in a little region, it's a fact about that little region. And the electric and magnetic fields are local. That is, supposedly in a little region, there's a fact about what the electromagnetic fields are. And if you just look at take all the little overlapping regions, right? Take an atlas that covers the whole thing and you settle all the local matters, you've settled everything. There is a global state, and the global state is nothing but the sum of all the little local states. And then you might say, yeah, but what about, I don't know, what about Newtonian gravity? And of course, Newton himself did not believe that was action at a distance. He thought there were some particles. You could say, well, there's also a gravitational field. That sounds like a local thing. You could talk about, how fast does the gravitational field change? You could put in a speed of light for it. All of that can be done in the context of all the ontology being local in space and time, in familiar three-dimensional or four-dimensional space-time. And in classical physics, in addition, all the dynamics is local, and that's what Einstein pointed out. He said, how do I know it's local? Because I write it down as differential equations over space-time. And differential equations, whether they're obtained or not, is a matter that's settled locally, because they're differential. So Einstein had this very strong intuition that ultimately all the ontology should be local and all of the dynamics should be local and furthermore relativistic in this sense. And so if I just propose a theory that has a non-local dynamics, right, you might get upset. Or if it has a non-local ontology in some sense, you might get upset. It's not what I grew up with. But, such is life, right? The claim here, the way I think about this is, okay, yeah, perfectly reasonable on that basis to look for theories that are local and separable until you run into Bell's theorem. And Bell says, unless you're crazy enough to deny this.
What's the second one?
Statistical independence.
Oh, right.
Or crazy enough to deny that there really are experiments whose outcomes, pairs of experiments done at space-like separation, whose outcomes violate Bell's inequality. There are people crazy enough to say that too. But unless you're going to do one of those things, okay, just give up on that. The universe is trying to tell you something. Listen. Now, so how do we get to now, let me just illustrate what I think. My view is to be and what David's is, and maybe I'll say a word about the difference here. I haven't talked about proper versus improper mixtures, which might connect this a little bit to whether moving from wave functions to density matrices makes any difference for this discussion. Just because I don't think it does, but just a technical. Okay, so as far as I can tell, right, what's my view? My view is there is a quantum state. It is real. It pertains to individual systems. There's actually only one of it, which pertains to the entire universe. Insofar as you want to define a little psi, right, a little psi for subsystems, it's going to somehow be definable from other stuff you have around, including the universal wave function, and if you're a Bohmian, other things that you've got around. But this little psi, these guys will be derivative ontology. They're things that you literally just define in terms of more fundamental ontologies that's there. So there is something represented by this. What is it? Well, my view is it's not a field. It may obey a wave equation, that's okay. But it's not something that requires a underlying very large dimensional physical space in order to exist. Okay? What does it require? Well, I think it's a fundamental kind of thing. I don't think it's the kind of thing that requires, in that way, something that's not a composite thing. The way the little psi is a composite thing. Then people ask questions like, well, tell me what it is. I mean, Barry asked before, is it a property? I don't even know what properties are. I mean, these normal categories from Aristotle don't help me, even if you say them.
I don't know whether that's a price.
Huh?
Is it a price?
Is it a price that I
No,
can't?
that is a price. That is this new kind of thing.
Why is that a price? I mean, again, I kind of, I like to walk this back and go back to when fields were introduced, right? I mean, think of all the Mishigas there was when Maxwell wrote down his equations. And then people said, well, there's really something to those equations. I mean, look at all the good predictions they make. But what's a field? It has to be, I need a mechanical explanation. I understand a field if it stresses and strains in a medium. Right? Then I've got all these vectors. What are those vectors? Oh, if there's stresses and strains in a medium. Well, what kind of a medium? I mean, you've got all these pulleys, and you've got these ropes, and you've got these springs, and you're trying to stick stuff together and saying, oh, wiggling this could wiggle that. And they, for years, these British physicists just had to have a mechanical model, right? And they struggled to make one, and they couldn't. Because it had to have properties that they couldn't realize using mechanics as they understood it, right? The Earth had to go right through it. Well, was there an ether wind? Was it dragged along? If the ether's dragged along, is there going to be a drag? Will the Earth slow down? Will there be aberration? All this stuff. And eventually, it seems to me much too long, people said, maybe these fields exist. They're just not like the things we are used to, right? They're not particles. They're not bits of matter. They're not stresses and strains. Now, British Proto-Barry could say, is that a price?
This is really unfair. Because they could explain why that was a price well worth paying. The question is whether the same thing could be shown here.
Well, the first question, is it a price? Is it a price for someone to propose there's something in the physical world you hadn't thought of before, and therefore Aristotle didn't have a nice pigeonhole for it? That seems to me zero price.
What's a new thing?
It's a new thing. Yeah, that's
see, but just like it's new that space has very high dimensionality.
Yeah, that's right. That's awful new.
That's new. And
That's new. My objection to that is not its novelty.
You said it's a price. That's not.
No. The price, what is the price for the high dimensional space? The price for the high dimensional space, I claim, is making the connection between what's going on in the physical ontology and what we are seem to be immediately aware of when we open our eyes, which is really important because physics is an empirical science, right? I mean, it is somehow supposed to be connected and under the control of or tested by data, experimental data. And those are reported in the language of objects in three-dimensional space moving around and doing stuff.
Tim?
Yeah.
Just, I mean, it goes without saying, I have lots to say here, but just at this, when you say making the connection between this high-dimensional stuff, and what do you mean by making the connection? I mean, if all you meant, and I presume this isn't all you mean, but if all you meant was defining a simple mathematical mapping between the two, of course you know how to do that. That's precisely what you alluded to when you called it configuration.
Well, I understand what you're saying. Of course, I know how to do that, to define exactly equal simple functions that give me entirely the wrong thing.
Right.
Right? If the space is really homogeneous and isotropic, then carving it into these subspaces can be done infinitely many ways.
Right.
And if you say, there's these infinitely many ways, one works well, and I say, hey, but all the others work crappy, who wins that debate, right? I mean, why does your one good outweigh all the millions of bad?
The space isn't all we have to start with, we have a dynamic.
Well, sure, I'm giving you a space, and I'm allowing you to say that this particle moves around it.
Right.
Now,
according to a particular dynamical law.
Yeah, but I'm going to give you the history of well, let me just ask you, right? So maybe we can put this clearly. If I held a standard kind of view about there being point particles in a low-dimensional space, I have some physics.
Right.
And I said fundamental ontology is a low-dimensional space, three-dimensional space, bunch of particles. And it's got a dynamics, and maybe I've introduced a whole bunch of things. Maybe I've introduced fields and God knows what to specify the dynamics.
Right.
But at the end of the day, a model of this thing will include as part of it these particle motions. Just that.
Right.
And I say, okay, forget about the rest of it, forget about the dynamics, just hand me that much of the theory. Can you look at that and tell whether a cat ended up alive or dead?
Wait, you mean the actual particle motions?
Yeah, the actual particle motions. No, not the laws, just the actual particle motions.
I mean, so look, I'm a Jungian, I guess. I'm someone who believes that from the actual history of the world, you can infer the laws supervene on the actual history. So asking,
I'm not asking you to do something fancy, David. I mean, you might think I can do a really circuitous thing. I can look at these particle motions, from the particle motions, rederive the Hamiltonian, rederive the dynamics, then make use of the dynamics to do blah, blah, blah. No, something much simpler. Can you just look at what the particles do and tell whether the cat ends up alive or dead? Answer yes.
Well, I don't understand. Oh, you mean the particles in three dimensions?
Yeah, billions of particles in three-dimensional space.
No, I don't think that's true, Tim. If it turned out that I poked this object and it turned into Donald Trump,
I'm not talking.
then I wouldn't say it was a cat.
I asked you, did the cat end up alive or dead? I mean, I don't even know. Take an actual cat. What?
I don't know if it's a cat.
If you don't know,
ask me if I could know if it's a
David,
cat.
if you don't know if it's a cat,
no.
unless you know about counterfactual pokings, then you never know whether anything's a cat.
Yeah.
Actual pokings you can see.
If you don't know about, if you don't have suspicions about how the counterfactuals would work out, yeah, you don't know very much about the world. That's true.
I would say, given that information, you can entirely painlessly answer a question like, does this correspond to what we think happened in the lab? Where what we think happened in the lab means the cat's either walking around or it's on the ground unmoving. and says nothing about what would have happened if you poked it. Because I don't think we have direct empirical access to what would have happened if we poked it.
No, that's certainly.
And I'm talking about accounting for the empirical data. So that means you have to think there's some empirical data that doesn't involve that. I may well believe the cat would not have exploded if I poked it, but that belief is a very complex belief that depends upon projecting and blah, 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 blah. But it has to be projecting from
it's part
something.
of believing that there's a cat there.
Hmm?
I take it those beliefs are part of what it is.
If I showed you the whole history, and there's like this collection of particles, I mean, we have to now pretend the cat's not eating and excreting and so on, and imagine, at least for a while, it's not doing much, but things cat shaped, right? Cat shaped, and it's like catting around and it's bumping into things and not blowing up, at least in reality. You're saying I couldn't tell that's, I mean, when you watch a cartoon,
right?
Do you think you can tell they're depicting a cat?
I think I can tell that they're intending to.
How can you tell? Do you tell that by their intending to depict that it won't blow up if you poke it?
Yeah, implicitly, sure.
Implicitly. So which part, if they wanted to depict it as the kind of thing that would blow up if you would poke it, what would they do?
We don't need to get stuck here. I'm not sure how we did get stuck.
We got stuck here because I was claiming that if I've got many, many particles in a three-dimensional space, I can make a connection to the empirical data.
Oh, I see.
In a very straightforward way. For you to do it, you at least needed, in this, if I think of this space as isotropic and homogeneous, you needed to add, you said, look, there's a very simple mathematical thing. If I slice it up a certain way. But if I slice it up a different way, there's an equally easy mathematical thing that gives me what I do not want. Something that does not correspond to what I see.
Sure. Yep.
Right? So I don't get why the existence of one of these things, which looks entirely arbitrary to me.
So the claim was, I mean, I'm sorry, Tim, I don't
Yeah,
want to go
it's
around
okay.
in circles. The point I was trying to urge on you was that I need the Hamiltonian to identify the particles in three-dimensional space as a cat as well. Look, take a simpler example.
You don't need it to identify them as cat-shaped.
If somebody just shows me the history of particles in three-dimensional space,
yeah,
I know nothing about the laws, okay?
Yes.
I know what's hot.
Is that what you're asking? Is that the question? Do you know what's hot?
Do you know what's hot?
You would, if you defined it as something like mean kinetic energy.
No, I don't define it.
Then I would say, just by looking at that, I would have no idea what heat was.
No, you have experience of heat from touching hot.
Yeah, this is not what I take the kind of data, right, that physics can actually make use of.
You mean physics can't make use of what's hot?
No, they use thermometers.
What's hot?
They use thermometers.
No, come on, Tim. You can crudely use your hands.
But you don't.
You're not gonna.
Do you think physicists are going around in their labs going, let me test this theory? No, they use thermometers, and thermometers out readouts can be read off of the configuration.
Okay, I know different physicists. I don't know what.
Have they burned their hands? I hope they're not like real high energy lab. Like, how hot is the beam?
I don't think that's going to settle questions about what's hot. I don't think, this kind of a movie that you're suggesting, if nobody gives me the Hamiltonian, no, if somebody does give me the Hamiltonian, I know exactly what's hot. I know if I can solve the Hamiltonian, I know it's going to make me produce utterances like that's hot. I know what's.
Oh, no, you don't.
I know even if thermometers have not touched these things, okay, I know that it would cause the thermometer to rise, okay? But for all that, I need the Hamiltonian, okay? And if a cat isn't the appropriate temperature, it's not a cat.
Okay. Yeah, so this is like, how far can we go? Would you agree that even without the Hamiltonian, you could tell whether at a certain moment this collection of particles was cat-shaped? as opposed to
Yeah.
say bowling ball shaped.
Yeah, you could, it seems to me you could tell that.
If it was bowling ball shaped, I could tell whether it's rolling or not rolling, headed toward the pins,
I think so.
the pin shaped things,
Oh, the pin shape.
the pin shaped things.
Yeah.
That it came into contact with the front pin shaped thing, which then moved and then came into the near vicinity of the pin shaped things behind it, which then moved. All that stuff I could tell without the Hamiltonian, right?
Sounds like it,
Yeah, I think this is going to give me all the data I need to test my physics. If you think I need the Hamiltonian, I don't understand how you think you do physics. If you think you need to know the Hamiltonian to get the data, how the hell do you get the data that argues in favor of the Hamiltonian?
Listen, you start out, we were talking about this all weekend. You start out with
We've been talking about this all our lives.
You start out with simple
In this room, we can
assumptions.
only talk about it for another 10 minutes.
Right?
In this room, we can talk about it.
Yeah, I don't want to
Let's
monopolize
then
it.
continue
We
for
do,
years.
you know, hopefully we'll have many years to talk. But by the way, Tim, just one, say, self-advertising. You just wrote a jacket blurb for a book.
Yeah.
That gives, that tries to argue for this in ways that you haven't even alluded to here, okay? So you shouldn't have written the jacket blurb. Because it tries to argue for this in ways that you haven't gestured towards in any way, shape, or form.
What do you have in mind?
A claim that, you know, I don't want to go into a big spiel.
It's okay.
It's too big a spiel.
Okay.
But I mean, that, you know, there was, you know, there's a book that you just wrote a jacket blurb for that was written because there was a thought that there was a completely different way of trying to make this plausible, okay? So it was even nicer of you to write the jacket blurb than I previously.
Well, so let me say this. Look, one of the questions is just the motivation. Right? Of course, you can try and spin out of you would like it to be motivated. At least your early motivations picked up by Alyssa in her book are, I want a physics that's separable and local. Right?
Alyssa has her motivations, but
those were your motivations in your original paper too.
Let me say one sentence,
Yeah.
and then I promise I'm going to shut up.
Yeah.
Take the sign that you circled, okay? You said David's motivations are something like this. I got a psi here.
Yeah.
Let's be flat-footed and say it's a field.
Yeah.
Okay, good. Even for the most old-fashioned motivations, that seems like a little bit of an unfair way to put it. Here would be a way to flesh out the earliest motivations that go back to this paper, which I guess is from 1996.
Yes, it
or
is.
something like that. You say something like this. I got a theory here. I want to know what its ontology is. I want to know what the theory is about. Okay. What should I do? Okay. Here's a flat-footed idea, as you put it. Not I see some mathematical object floating around somewhere in the theory. I say it's a field. Okay. Rather, you do something a little more elaborate, like you say, what is it in this theory? What is to this theory as particles are to Newtonian mechanics? Okay. Or what is to this theory as charges and electromagnetic fields are to Maxwellian electrodynamics? Or what are the equations of motion of this theory? The equations of the motion of.
Yeah.
Okay. It's not that psi is hanging around there someplace. It's not like taking E or pi and saying that's a field because there's a pi in there someplace. It's because this is playing, it's because this mathematical object appears in a particular slot in the theory that is at least superficially appears to be analogous to the slot that particle positions appear in Newtonian mechanics, or that field strengths and positions of charged particles appear in Maxwellian electrodynamics.
If one were to say, and again, I'm sorry, we're going to run out of time. If one were to say, because there are two versions of this. One is one where not only is this part of the ontology, it's in some sense all of the ontology.
That's the GRW.
That's the GRW version, or the Everett version.
Right, right.
Maybe it is Everett. Maybe
Right,
it's some
maybe
Everett is Everett.
To the extent that Everett is intelligible.
It's ontologically monistic.
Right.
This is
I mean,
all
you and
there
I
is.
agree about Everett, so, right.
The thing that has puzzled many of us was that you also think there's a kind, and what I specified was the kind of supposed Bohmian version.
Right.
Where there's just this single particle.
No, there's the single particle and the field.
Yeah, but yes, in addition to the field, there is an additional, but I mean, just the single
So it's
particle.
more analogous.
There's only one particle.
No, but so it's more analogous to asking of Maxwellian electrodynamics. Okay. What is to this bone theory as fields, as electromagnetic fields and charges are to Maxwellian electrodynamics?
Right.
What are the equations of motion, the equations of
Right,
motion?
David, I just want to repeat the question you asked. You said, what is in this theory that's analogous to the particles in Newton's theory?
Right.
Say, particle mechanics.
Right.
The normal presentation of the biowave theory, the answer is the particles, which are just like the particles in Newtonian mechanics, exactly like them, and there are lots of them. Many of them, they all live in a common
No,
three-dimensional
that's
space.
just not true.